Good morning, everyone. Morning. We'll be starting the first session of this day. And we have opening the session, we have Wertheimer, who will be telling us about SETI's future and where will Earthlings find the ET.
Thanks, Pedro. I want to talk to you a little bit about what might happen over the next 100 years of SETI. Before I do, I just want to thank David Tatel and Martine Rothblatt. David brought Martine out here. He was a friend of Martine's, and David and Jay brought her out here, got her excited about this place. It was Martine's idea for this meeting, and she funded it. So I'm grateful to both of them. And I'm also grateful to Jay and all the organizers that brought us here together. Thank you for that. Because there are 20 orders of magnitude uncertainty in how much communicative intelligence there is, it's very hard to predict when we might encounter ET. And what the Bayesian statisticians tell us is if you don't really know anything, you assign logarithmic probability to when we might find ET. I don't know if that's right, but if that's right, then maybe a 10% chance in 10 years, 10% in 100 years, 10% in 1,000 years, 10% in a billion years, 10% we never find them. And that would be the Bayesian approach. I want to start with the bad news. It's likely that we don't know what we're doing in SETI, that we're very likely doing the wrong thing. And the reason that's probably true is because if you look over the last 200 years of what we've been doing in SETI, the ideas have been changing and morphing. So, 200 years ago, we thought the best thing to do would be to have large geometric structures on Earth, triangles and squares, and ET would see that we knew about the Pythagorean theorem. And also a couple hundred years ago, people thought we could build big fires 20 miles across, circular rings of light, and ET would see that. And then we thought it would be a good idea to use large mirrors to reflect light to the Martians, sunlight in different sort of outlining constellations. And those were the best ideas of the time. And so now we sort of laugh at those ideas. But I think what it means is that in 200 years from now, people are just laughing at what we did. And they'll say, you idiots, you should have been using tachyons and subspace communication. And why did you do this radio stuff? So that in the last century, it was mostly radio, starting with Tesla and Marconi, and then the Navy looking at Mars, and of course Frank here on the Tatel telescope. There wasn't much RFI, and the head of the Navy ordered everybody to turn off all their transmitters so they could listen for the Martian radio signals. The nice way to get rid of RFI, you didn't have to have radio quiet zones. Here's the order coming down. Turn off all the transmitters. I think an example of this sort of anthropomorphic thinking is optical SETI. Well, first we did radio because we knew about radio. We didn't know about lasers. But when lasers came around, Charlie, and slowly people started to think about laser communication. That would be perhaps even better way to do intentional interstellar communication. I think radio is probably a better way to do leakage, sort of accidentally find their artifacts. But if you did want to communicate deliberately, I think it's now pretty clear that optical things are good for, and that was largely ignored for a long time. I think another thing we probably got wrong in the beginning was we thought life would be on just FGK stars, and those were the only things we should target. And now we know that you could probably have life on a lot of M stars and M dwarfs, and there are lots of places for liquid water outside the habitable zone. Now we know that there are liquid oceans in many places in our own solar system that are outside the habitable zone. So I think it's kind of naive to think that we know the best strategy, and I'm not saying we shouldn't do what we know how. You always got to do what you know best, but it's likely to be wrong. And so I think a multiple strategy is probably the right strategy. Look at a lot of different wavelengths, do targeted sky surveys, look for lots of different kinds of signals, and do a lot of different things. are probably better than doing a small number of large projects where you think you know what ET is going to do. And I just want to remind you that half of the important astronomy discoveries are serendipitous. I'm sure you know about pulsars and gamma rays, and a lot of these things are. And so I think it's probably likely that SETI will fall in that category. It won't be one of us deliberately looking for ET. It'll be a physics experiment or maybe some other astronomy experiment that finds some glitch. So we should be looking for glitches and anomaly. I think the machine learning anomaly detection is going to be interesting. You can apply that to large data sets and find little glitches in databases and unusual things. So a little more bad news before I get to the good news. That SETI is a dangerous thing if you're a radio astronomer. So this was the first telescope we used in the 70s to search for ET. And while we were searching for ET, that's what happened to that telescope. It used to be up here. And then we moved here to Green Bank. So this is me underneath that telescope. You can kind of see the structure here of that telescope. This is a 65,000 channel spectrum analyzer, got me into grad school. And while we were doing this experiment, this would happen to that telescope. So there, you might ask, why does that happen? And according to the World Weekly News, that aliens did not want to be discovered. But it actually turned out to be a good thing, because when that telescope was zapped by aliens, Berg came along and said, I want something even better. And so this thing got built. And now there are a couple of interesting SETI experiments. There's Serenity 6 that runs 24 hours on this telescope, thanks to some clever techniques developed here by Ron Madalena. And also the Breakthrough Listen is doing a great SETI program here, doing a lot of targets, a lot of not just stars, but galaxies, a lot of interesting things, and covering way more frequency coverage than has ever been done in SETI, because this telescope has this beautiful surface, and now they're putting lasers up here to make it even a better surface, so you can get up to 100 gigahertz. That's some. Let me switch over from bad news to good news. So the good news is the capabilities are growing. So even though we may not know how to look, the technology is changing, and so this is radio telescope. The capabilities, the sensitivity is doubling every 3.6 years for the last 70 years. If you look at the amount of the electromagnetic spectrum, the number of channels that we can cover. So when I was student, we had this 100-channel thing. Now we have 100 billion channels. The latest thing that we did on the FAST telescope. That's doubling every 20 months, going from 100 channels to 100 billion channels in 40 years. And I think that'll probably keep going. Computing technology is now, computers are as smart as a lizard or a guppy. And if that trend keeps going, that exponential growth, they'll be as smart as humans in 2030 or 2040. That's the singularity. That will be very good for SETI, maybe not so good for humans, but an interesting, it'll be very powerful. So what we should expect much more bandwidth, telescopes with 100 gigahertz of simultaneous bandwidth, maybe a million things made out of a million antennas, maybe a million beams looking at everywhere on the sky at once, very wideband feeds, phased array feeds with hundreds, maybe thousands of beams. So the technology is growing, and also I think our ability to maybe look for a much richer variety of signals will eventually grow as well. I wanted to say a little bit about some of the stuff that we're working on, and maybe other people could work on. So one of the things that we've been working on at Berkeley with the Chinese is a SETI experiment on the 500-meter telescope in China, and we're going to be doing a 3-year sky survey, and we have 5 instruments that are going to do the sky survey simultaneously. So it's not just a SETI survey, it's looking for fast radio bursts and pulsars and mapping galactic hydrogen and extragalactic hydrogen. And I think that'll be a very powerful instrument. It's a really beautiful 19-beam receiver, allows us to reject the RFI. Breakthrough Listen has been just started working at the Meerkat site in South Africa, which is a precursor to the SKA, and they're going to do 1 million 1 million stars, because you can form beams and point anywhere in the primary beam, and then that will eventually evolve to SKA in South Africa and Australia, we hope. It's not, SKA is not funded, but it's getting there. And so that'll be spectacular for SETI. Another thing that I've been excited about is this idea of looking for rare signals that maybe a flash once a month. And the problem right now in SETI is we use these telescopes that look at a little tiny patch of the sky, a millionth of the sky. And so if the signal's not on continuously, we're going to miss them. But we're going to look there and the flash is over there. And so if you want to look for rare transient signals, what you need to do is cover a big chunk of the sky simultaneously. So we've been working on that now. This is with Frank Drake, who's here, and Paul Horowitz at Harvard, and Shelley Wright's the PI at San Diego, and there are a bunch of us working on this thing. And what we want to do is build these domes that have hundreds of telescopes poking out of them, and each one covers about 100 square degrees, and combined they cover, each dome will cover about 10,000 square degrees. And we've got these new, the telescopes are very cheap, they're made out of plastic Fresnel lenses. We've got these new detectors that are used in medical PET scanners, positron emission tomography, that are really cheap, 1,000 times cheaper than what we had before. So we can afford to tile the whole sky with this thing and look for nanosecond flashes. So these new detectors that are used for medicine are, you can see individual photons and have nanosecond time resolution. It's something that we've been working on for a while, and Frank's been doing it, and I've been doing it, Paul. But now we have these cheap things have come out that allows us to look at the whole sky simultaneously. So that way we can look for these rare transients. Maybe we'll find some new. Then another thing that might be interesting is maybe you could do something like that in the radio. And people have been thinking about how could you build a telescope that could look everywhere at once, simultaneously look for rare radio signals. And there are lots of different ways to do that. But one of the ways that I've been looking into is using a bunch of small dishes. These are at Owens Valley, these are 5-meter dishes, and they're cheap, they're $10,000. And they've just got the money to build 110, and they're proposing to build thousands of these things. And what you could do is you could point them all in the same direction, and you have a spectacular antenna, but you could also point them in all different directions, and then you could cover the whole sky simultaneously and look for rare radio events. So this is a long ways off, maybe this 1,000 years from now, but eventually I think humans will be able to use the sun as a big telescope, as a gravitational lens. A lot of people have been talking about this, we don't know how to do it, but if you could do that, you would have a 10-meter resolution on extrasolar planets. I think you could, if you use it as a radio telescope, the sun is a big radio telescope, you could hear cell phone communication on extrasolar planets. That means that ET probably knows how to do that, so be careful what you say on your cell phone. I'm a little hesitant to justify SETI with spin-offs, but we haven't found ET yet. It's like NASA saying, give us more money because we invented Tang and Velcro or something like that. I'm a little uncomfortable with that argument, but we haven't found anything, so I just brag about these spin-offs. So I think one of the good things about SETI is that it's brought the public into this thinking about are we alone, and that touches on all these different aspects of science and gets kids interested in science and evolution and biology and chemistry, and we help develop this curriculum. There are a lot of people running the SETI at Home Screensaver. About 5 million people have 5 million people have downloaded this thing in 226 countries, engaged in a global science experiment. Andrew helped put together this kind of animation of the data going out from Berkeley. It comes from Arecibo and Green Bank, but it goes out to these yellow dots are all the different parts of the sky, sending out to all the volunteers. When they're finished analyzing the data, they send it back, the blue dots coming back. And that led to open source code that a lot of people now use to do all kinds of volunteer citizen science projects. So you can use your computer to do climate modeling and global warming, gravitational waves, planet searching. You can use your home computer to look for malaria drugs, cancer drugs, HIV drugs. black holes, protein folding. So there have been a lot of interesting kind of scientific supercomputing projects engaging the public. And some citizen science projects too. We have software to do that. Then another kind of spin-off came, these SETI instruments that we developed are very powerful digital signal processing computing capabilities, and we found a lot of people were using them to do other stuff besides SETI, especially in the radio astronomy community, looking at pulsars and doing spectroscopy. And we spun off that instrument part of SETI, and we formed this collaboration called CASPER, and we have about 1,000 people working together to build radio astronomy instruments, and a lot of the work was done here at Greenbank. They're important contributions to this here at this telescope. And out of that spin-off from SETI, these instruments that came originally from SETI instruments all led to all kinds of astronomy discoveries. The image of the black hole came from those instruments. Almost all the fast radio bursts have been discovered on these instruments, including the first one. A lot of pulsars have been discovered. You talked to Scott Ransom about that. Scott was telling me that this most massive pulsar that was found using these instruments is the most cited paper in radio astronomy because it
pulsars, just
in pulsars, yeah, because it hinges on the neutron star equation of state, and the physicists are interested in that. People found diamond planets. All kinds of stuff was found from these SETI-based instruments. It's used outside in medical research. I think our biggest spin-off are the students. And there have been about 100 students that have gone through our group. And I used to be very much worried about the future of SETI. It was very precarious because it was done mostly by people my age, you know, Jill and Frank and Paul Horowitz, and we're all getting on. And we were worried that there wasn't going to be a new generation of younger SETI scientists. But luckily, I turned out to be wrong. So Andrew and Jason Wright and Jelly Wright are sort of picking up and doing spectacular new work. And there's new money. So I'm optimistic in the long run for SETI. It's not as fragile as it used to be, thanks to these young people. So if you've been asleep, this is kind of a summary. No ET so far, we're still working on it, but it might be a while. And then the SETI home participants help us in a lot of ways. They help us write the code and get the bugs out, and they send money, but they also send in literature and music, and some of them send in haikus. And I wanted to read you a couple of haikus. So Paula Cook, a SETI home volunteer, searching for life, answers are revealed about ourselves. And last slide and last haiku, Dan Seidner, 1 million Earthlings bounded by optimism leave their PCs on. Well, thank you very much.
Are there any questions?
Yeah, I'm trying to understand how you parse up the spectrum. And when you say the word channel, am I to imagine like the resolution of a spectrograph and that's one bin?
Yes, that's exactly right. In SETI case, a lot of people think that the channels need to be very narrow because we're looking for very narrow lines that are not thermally broadened, that are not, as far as we know, they couldn't be caused naturally if it's not thermally broadened, not from a maser. Even masers are. So typically a channel is about a hertz wide.
But you're also talking about how broad the bandwidth is. That's
right, so we want a lot of channels so we can cover lots of bandwidth, but we also want each spectral resolution element, each channel to be narrow so we can respond to, if they are narrow signals.
And then you want to reduce the time as much as possible over which you're integrating.
Well, so this is very different. So there's a lot of debates about this. And some people think we should look for very short time signals, bursts, because they can stand out above the background like a lighthouse, a flash. And so some people, including myself, look for short time signals, bursts that stand out above the background. And then some people think that maybe it's on, so you can, if you want to stand out about nature, you can compress in time or you can compress in frequency. Both are interesting. So you want to do both.
So it's related to that, but in your search for optical pulses, what's driving your nanosecond time resolution that you mentioned?
So that is kind of similar to, so that if you want to resolve, if you want to get away from the background problem, you're pointing your telescope at a star and it's sending you a bunch of photons. But if you look at the nanosecond level, you never see 10 photons hit your telescope all at the same time. It's just sort of the star peppers you with photons and sort of Poisson arrival times. So it's pretty easy. There's no RFI background in the optical SETI. There's no analog of that. As far as we know, there are no false alarms. If you just do an experiment, did 10 photons hit my detector all within a nanosecond? That's ET.
It's empirical.
Is it even better at higher frequencies?
Well, we don't know what wavelength they might choose. We cover the whole visible band. We do some in the infrared, where a lot of people think that would be a good place because the dust goes right through the dust in the galaxy. But it turns out the detectors are quite a bit more expensive in the infrared. So right now we can do the whole sky in the visible. We can only do a meridian strip in the infrared, so we'll eventually cover the whole sky, but we'll do it a little bit at a time.
And UV is out of the question because hydrogen?
Actually, we could do it in the UV, but I think we're just starting where it's cheap. You know, like looking for your keys on a lamppost. But all wavelengths are interesting. I think every sort of octave has got equal probability. Yeah, Ted.
You didn't mention the Allen array. Can you say what the status of the Allen?
So that's been sort of resurrected, and I think maybe Andrew wants to say a little bit about that. He knows a lot more about it than I do.
Yeah, so it's recently refunded. I'm not sure who asked this question. We sort of undergoing a refurbishment.
Refunded by who? What?
A donor.
So there's money to improve the feeds and some operations money. The original vision was to build hundreds of telescopes. There's no money to fill it out, but it might happen. And the Allen telescope, in my mind, was very interesting from an engineering perspective. It sort of pioneered this idea of building a big array, and so I think it led to sort of things like MeerKAT and SKA, and maybe in this new resurrected state, it could get back to doing some interesting SETI and astronomy.
There are no more questions. That's time. Oh, sure.
You didn't mention the word aperture synthesis in the context of looking everywhere all the time.
Yeah.
Is there a reason for that?
In fact, we're starting to do that on the MeerKAT array and form beams. So this is a Breakthrough Listen project, which is just getting started. It'll be a commensal thing, so we'll let the astronomers point wherever they want. And in the primary beam, which is quite big, we can form beams, lots of beams, and look at places where we want to look.
You do that hardware in real time or?
In real time. Ask Andrew about that too.
Yes.
Let's thank Dan again. And our next speaker is Alan Voss, who will be telling us about searching for exoplanets using astrometric searches.
Thank you. So it just dawned on me that it's entirely appropriate that I give my talk following Dan's, because these are two areas of effort that have not really produced much of anything yet so far, but are extremely promising. So what you'll see in my talk that we may be on the verge of making a breakthrough, at least in astrometry. So this is going to be a talk about work that's been done by my colleague Alicia Weinberger and our postdoc Trios Padmaja using something called the Carnegie Astrometric Planet Search Camera, or CAPS-CAM. And I'll start off with a little bit of history. So astrometry is the way of detecting planets indirectly, just like radial velocity, due to the fact that if a star has a planet, it wobbles around the center of mass of the system. In terms of radial velocity, if you're trying to look for a Jupiter around a sun, it makes the sun wobble back and forth by about 13 meters per second over a 12-year period. In terms of how much it moves the location of the sun on the center of mass, for a Jupiter viewed from 5 parsecs, it makes the sun move up and down by 1 milliarc second. 1 milliarc second is about 1 centimeter, 1,000 kilometers. So it's a very tiny angle, but folks thought they would be able to measure that from the ground, and so astrometric planet searches began all the way back in 1938, when Peter Van de Kamp became director of the Scroll Observatory at Swarthmore. he started observing Barnard Star, which had been found by Edward Emerson Barnard. It's the fourth closest star to our Earth. The only thing closer are the Alpha Centauri and Binary and Proxima system. So it's 6 light years away. And so it's closest good because the closer you are, the bigger you can see the wobble to be. And Barnard Star is also an M4 red dwarf, 1/7 the mass of the sun, which is great also because the lower the mass of the star, the more you can make it wobble back and forth. So Peter Van de Kamp started taking data, 1938, and he, 24 years later decided to publish his data. So here it is, and 24 years of data, and he found a 24-year period orbit, he claimed. And there's the wobble and right ascension and declination based on X and Y on the sky. And this works out to be something like a 1.6 Jupiter mass object wobbling this rather small red dwarf over a 24-year time period. So this was in 1963. So it was like 2 years after President Kennedy said we're going to go to the moon. By 1968, this was accepted as a textbook example. It showed up in George A. Bell's classic astronomy undergraduate book. Yeah, Barnard Star has a Jupiter. Yeah, we sort of knew that. No big deal. You know, it's the one little paragraph somewhere in the book. So everything was accepted. Yeah, stars and planets. So what? Then along came George Gatewood, who did a PhD in 1973, and his advisor suggested, why don't you check to see if that Barnard Star claim is real or not? So they used completely separate sort of data taken with the Allegheny Observatory refractor. These are both old-fashioned refractor telescopes. And they had 10 times fewer data points, but they measured them with a newfangled plate measuring machine the U.S. Naval Observatory had just put together. And so they plotted their data, and they said, they said very charitably that we see no evidence of an orbit, of a wobble. And at the same time that this was published, the same year, one of Van de Kamp's colleagues published results using the same Sproul refractor for a different star called GJ793. And oddly enough, both Barnard Star and GJ793 wobble the same way. That's a hint. Either both have exactly the same planet in the same phase, or else something happened with the telescope. That is indeed what happened with the telescope. It turns out in 1949 there was a major change in the iron cell that holds one of the lenses, and they changed the photographic emulsions they were using. And then somewhere around 54 or so, there was a major lens adjustment. So that's why it went up and down, back again. So after 1973, the Barnard Star began disappearing from the textbooks. We had nothing for quite some time. So George Gatewood and I spent some time serving on various committees trying to get other astrometric telescopes up. And there were various things the Naval Observatory was trying to fly, which never got flown, and there were other missions that NASA was planning. But George himself was trying to do his own astrometric planet search. And he had trouble because he put his instrument on the Keck telescope, but unfortunately the Keck telescope has this primary that has to be rephased every once in a while. And every time you rephase it, you've got a brand new telescope, which is kind of like what Van de Kamp was facing. You don't want to change the telescope. So sitting together in 2000, we said, why don't we use the DuPont telescope down in Chile? Because he knew that even though I'm a theorist, I'm at Carnegie, so ostensibly I have rights to the telescopes. And sure enough, we managed to put together a proposal to build a camera for the 2.5 meter DuPont telescope, thanks to the NSF. Glenn, let me pass on. NSF partially funded this development of the camera. So it's sitting there on the Cassegrain focus on the right. Even though I'm a theorist, I literally was PI on this, and actually the strangest thing is I wrote the observing manual for this thing, so that's kind of strange for a theorist. But the key thing is we're using a new Hawaii 2RG detector, the same sorts of detectors that were being used on James Webb. And the nice thing about that detector is that it has a user-defined guide window in the center. So you put your target star in the guide window, because the stars we're looking at are nearby. We want them to have as big a wobble as possible. And if they're nearby, they're probably going to be bright compared to the background stars. So you don't want to take very short exposures to avoid overexposing. You want to be able to grind away for long periods of time in order to get good data on the faint background stars while reading out the data from the guide window for the nearby target star. So that's why this detector was such a wonderful detector to use for the camera. So we've been taking data now with that camera since 2007. Shreyas has been using a data pipeline that he first began developing based on the Gaia DR2 data, because Gaia is a European astrometric satellite following up after Hipparcos. It's doing wonderful work. We have a much longer data stream, though, than they do, so we should have the ability to find planets that Gaia will not be able to find. This just shows some of the early work on the data pipeline that Tree is working on, showing that, just look at this, the bottom black line. This is one where we're not trying to do a color correction. And what he's trying to do is to fit the fact that there are always going to be optical distortions across the field. And so you try to fit in some way of correcting for those distortions, and he used just x squared, y squared, or cubic, or quadratic polynomials to fit for it. And he found that, well, basically if you put in no more than a third order polynomial, you have a minimum in this Bayesian type criterion for whether you're doing good fitting. So, and then he also tried putting in color terms, because you can imagine stars of different types, as they go through more and more air mass, they have different aberrations associated with them. Turns out that for our camera, it's optimized for red stars, that we don't really need to put a color term in. So I'm going to show you some data I showed back in, well, let me say other things first, which is that the targets we're looking at are all late M, L, and T dwarfs, so they fall down to the tail end of the main sequence compared here to the Gaia, which is really interesting. And what's nice is that a lot of them fall on the bottom edge of this main sequence here. And this thickness is mostly due to two stars, binary star, which has the same color, but they're twice as bright because there are two stars there. So the fact that our targets mostly lie on the bottom side imply that these are probably mostly single stars. We do have a couple of binaries in there, some one or two that were known. We published a nice paper on EPSNDB based on CAPSCAM data. And a couple of previously undiscovered binaries, which we found, which we're going to be publishing soon. But the interesting thing is we've got a lot of real estate down here that's not really covered very well by Gaia. So we're hopefully doing something rather unique even compared to what Gaia can do, which is, Gaia is wonderful, but we're doing something I think that's very complementary to it. So here is one of our most interesting targets of all. This shows the wobble of the star over the 11 years of data due to, this is just the wobble due to Earth's parallax motion around the sun. And if you take out that proper motion and wobble due to the star and parallax of the Earth, and plot again an RA and DEC like you saw for the Barnard Star data, there's the best fit. There's the data points. And the Bayesian criterion went through and tried to fit everything, but it said, hey, this one here, this one just looks sort of funky to us. So kind of the Bayesian said, let's just throw that one out. And normally you don't want to throw data out. So you say, well, why is that one, why should that be thrown out? Well, this turned out to be a very nice double-blind test because we fed all the data in. Then after the Bayesian kicked this guy out, it went back up to the observing log and realized that that particular epoch was taken. For some reason, I took it late at night when it was near the horizon, and it was sort of a very high air mass data point, which means it's going to be crummy. And so from that point of view alone, one could have said, well, let's just throw that one out. But anyway, Bayes threw it out for us. And if you believe this, then this could be the first detection of a planetary mass object to, unfortunately, not a star. The primary is a brown dwarf, but could be the first detection of a planetary mass object around a single star. Roughly 1.5 Jupiter masses, eccentric orbit, out at about 2 AU with a 9-year period. So that's kind of interesting, but we're still working on it. We're not quite sure if that's reliable, so we're not quite ready to publish it. But if it's real, it should produce a rather large radial velocity wobble, which is good because that means we can be either confirmed or disproven by a radial velocity measurement. In fact, there have been radial velocity measurements taken on this target by Cullen Blake with near spec unkept. But you can see the radial velocity precision on this rather faint red dwarf star is not very great. If you really want to be a believer, it sort of follows a slow decrease like is inferred by our astrometric solution. But unfortunately, we just sort of, right now we just sort of missed the most exciting time to do a radial velocity measurement. So if this is the correct thing, the best time to do an RV confirmation of this would be another 7 years or so from now. So maybe that'll be confirmed, or maybe it'll be disproven by radial velocity in the future. But at least it's confirmable. So if these things are right, we have roughly half of our stars seem to be showing a wobble, and that's these orangish triangles plotted here on the background data field of, these are all the targets from the Nexi catalog as of last July that have a mass. So it's not just the Kepler stars where we have a size. These are the ones that have a Kepler size as well as a RV follow-up. So they're mostly RV planets with an plotted with M sin I. So these objects we're seeing seem to plot right in where RV has found a lot of other planets. They're not very bizarre from that point of view. But what's interesting is that, as I showed from the Gaia color magnitude diagram, we're in a region of demographic space that's really not very well explored. There are some low mass M-dwarf stars that have super Earths from radial velocity, a few direct imaging possibilities, but if our guesses are right, then we found a whole cluster of planets out here, which is very interesting, I think, from the question of exoplanet demographics. Now, all right, this one's kind of strange. Let me just skip that one. Oh, what happened there? Can someone help me with this? I'm not quite sure what happened. You can get me back to that slide there that's highlighted. There's the mouse. Okay, thank you. All right, so if this is real, this is a sort of, in discovery space, where we can find things above this line that have with a 0.25 milliarc second accuracy, signal noise of 4. We can find anything up around here. Sorry, so that's fine, but what does that have to do with habitable planets? Well, the interesting things about these, if these things are real, is that they may be sort of analogs of our solar system, where we have outer gas giants and inner habitable worlds. So for low mass stars, the habitable zone for a 10th of a solar mass star is around this sort of center major axis, this is sort of a late M, this is an early M. So there's plenty of room inside in terms of orbital packing to have Earth-like planets inside. So whenever we find a gas giant around one of these nearby M-dwarf stars, those hopefully will be high priority targets for searching by other methods to see if there are Earth-like worlds in there as well. Now, astrometry with CAPSCAM is not doing too bad. We're sort of at the quarter of a milliarc second level, and we're quite comparable to what's being done on the Gemini telescope. This is actually from a very nice report that Eduardo Bendek put together for NASA. So we're sort of at the level of what Gemini can do. There is an instrument on the VLT that Johannes Salmon put together, which does quite a bit better. And he's done some searches of stars, but he's yet to find any wobbles that are of Jupiter mass objects. For the future telescopes, TMT, the European Extremely Large Telescope, they will do really well as well. They're sort of down to the Gaia level of precision. And of course, if they can keep operating for decades, they'll be able to find very long period astrometric planets. But even these numbers are nowhere as close to what you need in order to find an Earth. And so if I hinted at earlier on, the extreme precision radial velocity folks may have a problem, not with instrumentation, but with the stellar jitter of the lines. And so that's one of we really want to have these masses of these guys, right? We don't want just to have the radii of the transiting planets, we want to have their masses. And so we want to get masses, and astrometry is the other way to get masses. If you want to do an Earth at 10 parsecs, you're at 0.3 microarc second, that is the signal. And so you want to do better than that. So the NASA long ago put together proposals for a SIM mission, Space Interplanetary Mission, that would get to give you a signal noise of 10 basically on an Earth at 10 parsecs. Unfortunately, SIM lost out, in part lost out because of the funding increases needed for James Webb Space Telescope, but it also lost out because Astro 2010 did not rank it high enough for it to appear above the water line. So SIM isn't out there, but maybe someday we'll have to rethink space astrometry if we do not think that stellar jitter can be overcome by radial velocity. And there is, of course, stellar jitter for astrometry as well, but again, Eduardo Bendek put together this report where he basically concluded through these lines of evidence that stellar jitter is not a showstopper for Earth-like detection. And so if we can't do it from the ground with extreme precision radial velocity, we may have to eventually start thinking about going to space to get the masses of these objects. That's what I have to present to you. Thank you very much.
So there's an interesting space interferometry experiment that you may have heard about that's being funded at the study phase by Breakthrough. The PI of that is peak Tuttle. And it takes advantage of the fact that Alpha and Beta Centauri are close together in the sky, and if you measure the relative separation of those two stars, you have a chance of seeing an Earth-like exoplanet. They believe that they can achieve with a small telescope an accuracy that is a order of 1 microarcsecond. So that's something to look at and stay tuned for.
Yeah, I was not aware of that, but that technique is actually the same technique that was used to make the claim that was mentioned earlier, that the Palomar test bed interferometer was again, it was not a single telescope, but it was an interferometer looking at a very bright binary star system. So yeah, I did not know about that, but that sounds very interesting. And yeah, at this point, we really want masses. We should try everything.
Oh, Alan, there's a proposed space mission, I think it's an ESA mission called NEAT, which is like a 1 meter telescope that would do very accurate astrometry. Is that still a proposed
I don't
mission?
think it has much of a chance right now. I think Mike Shaw was involved in this. Mike Shaw was the architect of SIM. Folks have been trying to get other space telescopes up, but as far as I know, I'm not sure when the next competition will be for European missions, but I think things are pretty much set for the next 10 years or so. So I don't think it has a chance of flying in Europe, but maybe someone else can know more about it. But yeah, like I say, if we can't do it with Doppler, then astrometry is really going to come back to people's minds to get the masses.
I was curious about your color magnitude diagram. Things are really hugging the bottom. Have you done anything that is selecting for low metallicity, which is how I would have interpreted all of your stars hugging the bottom of the Gaia main sequence?
No, not.
Not for like high proper motion or anything like that?
No, the only criterion is that they're close by. And there are not very many high proper motion in the sense of not passing through the disk something. I don't think we have anything quite like that.
Okay.
It's purely selected, everything within basically 15 parsecs we could find. You get beyond 15 parsecs, we drop you.
Now, your points there seem to be some, you showed in what you've looked at, you see some wobbles or tentative wobbles or interesting wobbles that haven't published it. But you've also probably looked at those same stars in the Gaia DR2 to see if your wobbles are confirmed by theirs, and presumably that would give you a much bigger, better signal, and or is that not the case?
Well, Gaia shows excess noise for a certain number of stars, and the stars for which they fit the proper motion and parallax,
Yes.
and then every star they have a little catalog showing, well, these have excess noise. So that could be due to a long period binary out there. There are people who are searching the Gaia catalog for the excess noise stars, seeing which ones are binaries.
Gaia haven't published their orbits yet, Charlie. So
Yeah, exactly right. They've just basically done proper motion and parallax, just step one. So, but yeah, some of in fact, this star 8BB1 does have excess noise in Gaia, and so in our data pipeline, we're trying to make sure that we know what the source of the excess noise is. The question is that excess noise due to a real wobble, or is it due to some instrumental or systematic effect we don't know about?
So if I've understood this correct, Gaia is now publishing their orbits as excess noise.
No, they're publishing proper motions in parallax and then saying, well, after we fit that, there's still something sitting over here that we can't account for. It's a question mark. It
they
could
will
be real.
post the orbits in DR3 and DR4. But that's in a couple years.
So eventually, we do want to be able to merge our data with Gaia, because that would be the strongest thing of all. But right now, the versions of the pipeline we're working on are taking Gaia out, because we're sort of thinking we're using Gaia to correct our optics. Gaia has its own set of problems, so we're sort of conflating two different sets of whatever Gaia's problems are and our problems. So right now, we're trying to do a pure CAPSCAN fit. That's why we haven't published that yet. We're trying not to do what Peter Van de Kamp did. Because there's actually another astrometric claim by Jacqueline for EV8 that they predicted a very large amplitude, a radial velocity wobble, and within a year, Doppler folks said it ain't there. So we're trying to avoid that.
There's no more time for questions, so let's thank Alan. Next speaker is Natasha Batalha, who will be telling us about TESS and the James Webb Space Telescope and the prospects for astrobiology.
Cool. Yeah, so I'm going to to be talking about TESS and JWST, specifically the prospects for astrobiology in the next, however many years it takes to get JWST off the ground. I want to start, though, I think sometimes when I give these talks about, JWST and the prospects for astrobiology, it gets a bit doomsday. Because we're on this straight and narrow path where, TESS has discovered that planets are pretty common. It's found several planets in the habitable zone. TESS is going to go in and find those planets that are closest to us. And so the next thing that everyone is just super excited about is to go in and actually measure the compositions of those small terrestrial planet atmospheres, and of course ask questions of whether or not there are signs of life there. And so, in this talk, I'm going to be specifically focused on observing terrestrial type planets or small temperate planets with JWST. But of course, we should always bear in mind that JWST is going to do a whole host of super interesting science for some of our, puffier, hotter friends. Characterizing large populations of exoplanets by looking at their atmospheres, understanding sort of universal chemical processes that happen on these types of exoplanet atmospheres, leveraging atmospheres to improve our understanding of origins of exoplanetary systems. These are all things that we haven't really done with HST, because with HST we have pretty limited precision. We're only looking from 1 to 2 microns at pretty low resolution. And so our eyes are really going to be lifted, or the curtains are really going to be lifted in this era of JWST, even if, we don't discover life with JWST. Okay, but the question still remains, for TESS, how many small planets do we expect to find around bright stars? And of course, TESS has already started to rake in some new exciting discoveries. There are several new planet candidates. Now, for small planets around bright stars, there's pretty uniform consensus that for planets that are smaller than around 1.5 Earth radii, brighter than around a K of 9, TESS is going to find about 3 or 2 plus or minus 2 planets in this regime. Now, of course, if this seems like small numbers, but if you bump up the number to about 2 Earth radii, this increases to about 10. And if you decide, maybe we can go a little bit fainter, this goes up to a few dozen. So TESS is going to certainly bring in exciting new planets. All of these temperate sort of habitable zone planets are going to be, of course, orbiting M dwarfs, which will still be very exciting for JWST. Of course, TESS isn't the only mission that is going to be discovering planets in the next few years. There are several other observatories which have already produced really compelling targets for JWST observations. I came late, so I don't know if we've already talked about the TRAPPIST system. Moderately, okay. So, of course, we know the TRAPPIST system, really exciting target, has around a very small star. There's 7 Earth-sized planets. The star is almost the size of Jupiter, so it's pretty cool. 3 of the planets are nominally in the habitable zone, and what's great is that TRAPPIST is viewable for 99 days of the year, so you can actually observe it quite frequently with JWST, and actually all of the targets, or almost all, I don't know if the outer planet H and G are, but most of the other planets are already slated to be observed with the guaranteed time observing, spread across all of the guaranteed time observers. So everyone kind of has their own strategy for going and observing these planets. I think we're doing phase curves or emission spectroscopy of the hotter planets, and then transmission spectroscopy of some of the habitable zone planets, so D, E, and I think even F. So this is going to be exciting new territory, specifically because if you look at planets D, E, and F, they kind of have similar insolation fluxes to Venus, Earth, and Mars. And so just getting some cursory transmission spectra of these 3 planets is going to be incredibly interesting as an initial scope to see kind of and compare the compositions of these 3 planets. And so the question, of course, becomes, for something like TRAPPIST, this is kind of a gold mine in terms of transmission spectroscopy, what can JWST do for something like this? Now, for those who don't spend their lives looking at transmission spectra, this is kind of just to wrap your head around the sizes of signals that we expect. So at the top, you're looking at a hot Jupiter transmission spectra. And of course, this is wavelength. So this covers 1 to 5 microns, which is primarily where we're going to be looking for transmission spectroscopy in JWST. There's an additional band which takes you out to 14 microns at low resolution. That's the MIRI mode. But you can see that in all of these transmission spectra with JWST, we're going to be looking at pretty broad band spectral features. So for hot Jupiter, you see those kind of whopping huge rotational bands of water, carbon monoxide, carbon dioxide. As you get to some of the cooler gas giants, you see methane features start to appear. And then at the very bottom here, I'm showing a simulation of what an observation of a true exo-Earth might look like. And I haven't told you anything about what the observing strategies of this is or how much time this would take, but your initial gut feeling looking at this kind of should be the takeaway message that this is going to be really difficult. And for an Earth-like planet, you can see that the largest features that you're looking at are these carbon dioxide rotational bands that are around 4.5 microns. And the other thing you should notice is that I'm not showing anything, just a few microns short of 1 micron, where, of course, oxygen is sitting. And the problem is that the JWST precision, short of 1 micron, starts to drop dramatically. And so it's going to be very difficult to get very low resolution, small bands like the oxygen bands that are sitting here at 1.7 microns. Okay, the other thing is I'm going to start showing you a bunch of simulations of what the expected precision should be at various J magnitudes. And so something to keep in mind is that these hot Jupiters or warm Neptunes, their expected signal sizes of the molecular bands are going to be something like hundreds of ppm, so they're going to be pretty large. Whereas for terrestrial planets, we're going to be digging for signals that are in the tens of ppm, so it's going to be significantly more challenging. Okay, so here I'm showing, again, this is single transit spectral precision as a function of J magnitude, so how bright the star is. These are all bin to R of 100, so you can actually compare the different observing modes of Webb. And I'm just showing a little sampling here. So the near spec GRISM, which goes from 1 to 2 microns, the same spectral range as HST with C3. Near SOS, which takes you out to about 2.7 microns. The PRISM, which is great. It gives you the whole 1 to 5 micron blip in one go. Of course, it saturates really early at around J of 11. And then MIRI on the other end, which takes you from about 5 to 14 microns. So a couple things to notice is, these are on different scales. So towards the MIRI wavelength ranges, we're going to get significantly less precision than we do at around 1 micron. And especially the MIRI detectors might start to cap out at around 50 ppm. And so it's going to be incredibly difficult to do any sort of transmission spectroscopy, potentially with MIRI LRS. But you can see some of these bands, our hot Jupiters, again, are sitting up here. Their spectral feature sizes are, several hundred ppm, and so they're going to be super easy. We're very low-hanging fruit. We're going to be able to do them very quickly within 1 transit. Now, for the Earth-like planets, they're always going to be down here in the weeds, and this isn't surprising. We've always known that we would have to stack several transit observations to detect some of these Earth-like features. And when you look at this, an immediate question you might have is what is happening down here. Of course, we want to observe, we want to find these planets around the brightest targets possible. I told you that, we might detect 3 Earths in this regime, so why can't we get precision that, that doesn't cap off like that? And you might think that this is actually, some sort of noise floor that is happening on the detectors. What's actually happening is as you get toward these really bright targets, your observing efficiency, your duty cycle of the instrument actually starts to decrease significantly. So JWST observes in this sampling up the ramp manner where you start by resetting your detector, you take a bias frame, and then you take your science frame. And so for these very bright targets where you can only fit in maybe 2 groups, you saturate at the second group, and you're only getting 33%. 33% of your observation is the time that you're actually getting useful science photons. And so that's why you get this cap. Whereas out here, you don't saturate as quickly, so you can fit in several different groups to your observation and increase your observing efficiency. And so if, and I'll tell you why I'm pointing this out, if we had perfect efficiency, you could actually get down much further towards, this range where our Earth spectral features are, and it would be very, very helpful in doing some of this terrestrial exoplanet science. And the reason that I mention this is because there are options for cycle, maybe not cycle 1, but there are options in cycle 2 that can actually improve this. If you have questions, let me know. I won't be able to go into what they are, but we could potentially get to closer to 100% observing efficiency with Webb in maybe cycle 2. Okay, so then the question becomes, if we can get this kind of precision, what can we actually do? So to answer this question, I'm just going to make a bunch of hypothetical transmission spectra of TRAPPIST-1e, which is one of the planets in the habitable zone. And so here are, a bunch of water-rich, nitrogen-rich, carbon dioxide-rich spectra, where I've injected some trace gases into those. So, 1% methane, CO2, nitrogen in a water-rich atmosphere. Likewise for nitrogen-rich, carbon dioxide-rich, and we're going to assess how well we can constrain both the temperature and the composition in each one of these cases to get an idea for how well Webb would do. And so this is, so here you're looking at the uncertainty on temperature as a function of the number of transits that you stack together. And then here is the uncertainty on the abundance, the mixing ratio on water, carbon dioxide, and methane, and the colors are in a hydrogen-rich atmosphere, and a carbon dioxide-rich atmosphere, and a nitrogen-rich atmosphere. The width of the curve is for different kinds of cloud coverage. So of course, if you have a completely clear atmosphere, it's going to be relatively easy to detect spectral features. Of course, we know with Hubble that clouds are, and in our own solar system, clouds are prevalent everywhere, right? And so that's what the width is. Now you can see immediately that detecting water in a water-rich atmosphere is pretty simple, and you get relatively good constraints. Same with detecting carbon dioxide in a carbon dioxide-rich atmosphere, but it's much more difficult to detect the trace gases on top of the dominant absorbers. And so the takeaway here is that for temperatures, and in a pretty optimistic case, you might be able to constrain temperature plus or minus around 100 degrees, which is not great, but it's not horrible. And for mixing ratios, best case scenario, if we have relatively little cloud coverage, we're looking at constraining compositions with about half a depth. But most likely, because there will be cloud coverage in a lot of these planet atmospheres, we're going to be looking at something that's maybe, one or two decks. Okay.
Can you tell me what DEX is? Sorry.
Oh yeah, sorry. So for it, like 1 order of magnitude. So for example, if you had 10 ppm or 10 to 1e to the 6th minus 6 water composition or water mixing ratio, your constraint would be 1e minus 6 plus or minus. That would be like -6 plus or minus 2. That makes sense?
Yeah.
Okay, cool. Okay, so the one thing that you notice in all of these plots, though, is after the 10th transit, or after about the 10th transit, the dominant absorber is always detected. And I think that this is a great takeaway because it means that, even in, maybe we won't get all the trace gases, but for JWST in these initial observations, we're going to get a really good scope or a really initial cursory look at what these atmospheres might look like. And I always say that, there are of course going to be other cases in which, by the 10th transit, we just don't see anything, right? Either there's going to be an insane amount of cloud coverage, or for all we know, that planet atmosphere doesn't even have an atmosphere. And so at that point, though, I would say we should move on to another target. Of course, there's going to be more than one terrestrial planet atmosphere that we try to look at and try and see, how many things that we can detect. You can do the same thing, same exercise for thermal emission. Thermal emission with MIRI, like I alluded to earlier, is going to be much more difficult than transmission spectroscopy. So you see in a lot of these cases, you don't actually really detect anything, and you're only going to be seeing kind of an initial kind of constraint on what your temperature is. Basically, you're just going to be seeing a black body of what these temperatures are. And these planets are so cool that they're very difficult with MIRI. Okay, so the capabilities are you always detect the dominant absorber. This is great, and the challenges are going to be emission in these trace gases. Now, I motivated this in the beginning by saying, oh, well, this is really interesting. D and F, they look a lot like Venus, Earth, and Mars. So for Webb, could we distinguish between a Venus, an exo-Venus, and an exo-Earth? What would those two planets look like if you can detect the dominant absorber? And so this was really, I don't have the citation here, which is really bad of me. This is Joanna Barstow's work. And she created simulations of Venus kind of transitioning into the Earth state, and that's what you're looking here, these spectra. And from 0 to 5 microns, this is where I said was going to kind of be the region where we're going to be doing transmission spectroscopy, and this is where precision kind of tapers off because of MIRI. And you can see the initial thing that you see is from this 0 to 1 or 1 to 5 micron region, Earth-like planets and Venus-like planets look really, really similar. And the reason for this is the dominant absorber. Notice how I was saying the dominant absorber and not the dominant background gas, because nitrogen in Earth's atmosphere doesn't have spectral features, or doesn't have, I should say, broadband spectral features. The dominant absorber in both cases is carbon dioxide. And so when you actually look at what the observation of both of these planets will look like, it just looks like, nothing from about 0 to 2-ish microns, and then you get a little carbon dioxide bump, and then a bigger bump at around 4.5 microns. But I would still say that even looking at several of these planets and seeing that they all are maybe dominated in some way by carbon dioxide, I think will still be very compelling, a very compelling thing to do in the realm of astrobiology for JWST. I had a little bit more doomsday message, but I'm out of time, so I'm going to stop here. And if you're interested, I can tell you the last bit of bad news.
We have time for one short question. Yep.
What's the last bit?
So the last bit of bad news is that our ability to constrain atmospheric composition is directly tied to how well we know the masses of these planets. And so this is just a spectra showing these are two spectra with completely different water compositions, but different gravities. You can see that they look identical. And if you actually do the exercise and see how well you can constrain planet atmospheres as a function of how well you know the mass, if you don't know the mass at all, you really can't get any sort of idea of what the composition of the atmosphere is. And it turns out you need something like 50% or even a 20% mass accuracy to be able to do good atmospheric compositions. And getting those accurate masses is going to be very challenging. So. Yeah.
I'm curious, what's the rough number of Earth-like targets do people have collected for, potentially?
Oh, that exists now?
Is it a few, or is it 10? Or
Currently it's like a few, so it's not a lot. Yeah, a few bright targets. So, and if you look at what TESS is potentially going to give us, we're looking at maybe 5 or so, like really small numbers. So if you could do in JWST's lifetime 10 transits of 5 planets pretty easily. Yeah.
Thank you. Our last speaker for the session is Jeff Kuhn, who will be telling us about looking for Exo-life from the ground.
Good morning, everybody. I have a hard task, I guess, which is to convince you that exo-life might actually be detected from the ground before it is from space. So this is a project that started for me about 5 years ago. A bunch of people have gotten involved over the years. this fella right here was a person of means who came to me when I was the director of the IFA Maui and said, if I gave you some money to put together a team to look at the question of what would the optimal exoplanet optical instrument be if you're going to use it from the ground, he did that, and we put together a group that had some serious people. The head of the company that built Keck and Subaru is a very experienced engineer. He was part of the team. Svetlana Berdugina was part of the team. She was our exoplanetary science representative into the community. And then a large group of engineers and a few other astronomers. And for the last few years, we've been pondering that question. I think there are 4 messages in this talk. The first is that there are a lot of things that we could learn even with moderate signal problems with a ground-based optical instrument. I want to amplify on some of the background stuff that we've talked about at this meeting, but we haven't shown some quantitative results. I think that it's quite true that many exoplanet studies, and I think Russ made this point, are best suited from the ground, and I'll try to explain why that is. The Wright Exoplanet Telescope doesn't really look anything like the current world's largest telescopes that the broader astronomical community is building. And I'd like to give you some insight into, if you had $100 million, what that telescope would look like if it were dedicated to exoplanet studies. And finally, I think that we've gotten far enough in what we've done to demonstrate some of those technologies, enough to be able to say that if we had 5 to 10 years and a little bit more money, we could actually build something that could do some of the things that I'm going to talk about. So the first interesting point is that if you look just at the reflected or the thermal emitted light from an exoplanet, if you could build a telescope that could isolate that light from the light of the star, solve the scattered light problem, it's a telescope that might have that sort of angular resolution on this scale, where the exoplanet is a tiny dot in the center. So if you could do photometry with a telescope like that, you might, over the course of 1 exoplanet year and maybe 100 exoplanet days, get a light curve that looks something like this. And what we did was we put the Earth at the distance of Alpha Centauri, and we gave it an inclination, and we took the known albedo distribution of the surface of the Earth, and we looked at the integrated reflected light that you would get based on that telescope that I just showed you, or at least the resolution. This is the input. This is the light curve. The signal to noise that we had in this data was about 200. Now do the inversion problem, and that's the picture of the exoplanet that you could extract. So even though your resolution will never, in many generations, build a telescope that could directly resolve that structure, from a light curve inversion, we can deduce a lot. In fact, we can deduce continents and structure that we might not have expected. It's a very robust problem. If the signal to noise were only 20, the inversion still gives enough information to learn about continents and oceans. You might ask, well, so in the case of the real exoplanet that's at the distance approximate, it's phase locked in some way, does everything break down? And the answer is no, it doesn't, because the amount of light as the planet orbits, even though this is an exoplanet that's inclined and rotating with the same rotation period as its orbital period, we get to see a different sample of the reflected light off of the surface. And that inversion problem still gives us enough to be able to learn something about the albedo and the structure of the planet. Now, there are obvious generalizations of this. Split the light up into different colors and look for forests and look for deserts, or look for heat islands due to places where it's hotter than the ambient background. And we played those games, and I'll just say that it's a robust problem, and I think there's a lot to be learned with moderate signal to noise, visible and infrared photometry that you could get from a telescope that can separate the light of the exoplanet from the star. This just shows at one point in the meeting we asked, well, how do we know the inclination or the orbital parameters that describe the exoplanet? Even without knowing what the surface structure is, just by looking at the light curve, this is a chi-square plot that shows how we can isolate orbital parameters just from the overall light curve with some inversion activity. So there are two elements to the photometry problem. One is looking at the thermal emission, the other is looking at the reflected light. It was a surprise to me to realize that even with our civilization, we consume about 0.05% of the total power that the sun projects onto the Earth. We're not all photovoltaic, but the power that we use from fossil sources and nuclear sources and all other sources is a significant fraction of the total power that the Earth absorbs from the sun. So let's normalize all those power estimates by the flux that the Earth receives from the sun, and all of that power ends up in heat, one way or the other. And ask the question, could we begin to see astronomically the heat signal of civilization? And you should know that heat islands are already, this is so I'm from Michigan, these are not really big cities, but here's Chicago and Detroit's over here. The temperature contrast is several degrees, up to 10 degrees, out of a 300 Kelvin source. If we had any resolution, or if we used the rotational signal, you could say that actually the contrast, the thermal contrast, is in the realm of astronomical measurements. And what I was showing here was that the total power consumption, which is not distributed uniformly over the surface of the Earth, is at, so this is the total power of the sun on the Earth, is at it's 5 times 10 to the minus 4. It's quite a bit less, or quite a bit greater than the optical power production. So you've heard people talk about, well, let's go look for civilization by looking for the skylights that are against the background of the night side of the planet. And that's a very difficult problem. The thermal signal, on the other hand, is something which is almost doable astronomically. So if you give that we're building an optical system which is diffraction limited, whether it's in space or on the ground, you probably know that the ability to detect a weak signal in the presence of a background improves like the 4th power of the diameter of the aperture, assuming that it's diffraction limited. There's 2 powers from the area of the aperture, and then there's another 2 powers from the angular resolution of the source against the background signal that provides the signal to noise in this estimate. So there's a huge advantage if we have a diffraction limited telescope in increasing the aperture. There's another advantage if we're interested in some kind of statistical study of life or exoplanets or life on exoplanets. This is an angular resolution problem, and the angular resolution of the telescope scales like the 1 over the diameter. So the volume of space that we can sample also increases like the cube of the diameter. So there are huge advantages to this problem to be able to build something which is very big. So thinking about the landscape of all of the world's largest telescopes, this is a bird's eye view, and the ones that you know of are the ELT and the TMT. These are the Keck telescopes. The distinguishing feature of all of these large telescopes, the world's largest telescopes, is that they have many, many, many signals. And the problem with those telescopes, here's a picture of all of them, you've seen them. In space, we'll have, again, segmented telescopes, but we won't have the atmosphere. But I don't think the atmosphere is the problem, because we can build telescopes now that don't see the scattering properties of the atmosphere. So one of the issues is going to be the segmentation. The cost of the telescope versus size is the other killer in trying to build larger telescopes. It turns out that if you look at telescopes that are built, here's the Keck telescope, and this is aperture here versus either moving mass or area. We find out that for all of these planned telescopes, the price and the moving mass all scale with the diameter squared. That's a very optimistic prediction. It means that basically we're taking a mirror and we're replicating it to make the larger telescope. The moving mass of the telescope and the area are all scaling, and it turns out that by all of the cost studies, the cost of these scales with the moving mass. So some of us that are old enough remember the overwhelmingly large telescope, which was, for 5 years, a serious topic of conversation, mostly in the European community, to build a 100-meter telescope, and the costs were at $10 billion. The 30-meter telescope, By the way, we still are not getting up the mountain. There are two roadblocks, one manned by the native population, the other manned by the police. And neither one of them are letting anybody go to the summit. But when it is built, that's a telescope that will be at least 1.5, I think the estimates now are closer to 2. It's 30 meters. The European Large Telescope also lies along this line. The important number to remember is that the scaling for all of these is that the moving mass is about 2,000 kilograms per square meter, and the cost is between roughly a half or a third and $1 million per ton. So all of the world's largest telescopes that our community, the astronomy community, is considering fall along this line, and these are the numbers that characterize them. In contrast, we just saw a 100-meter off-axis telescope, which had a cost which was $0.013 million per ton, and it was 800 kilograms per square meter as opposed to these numbers. Why was it so much more of a bargain than the optical telescopes? Because the surface roughness was not optical, but it was pretty darn good. I couldn't believe that you're actually getting to 200 microns RMS. But this is an example of a telescope that we'd like to build just a little bit better with the surface for these optical programs that we're going to talk about. What's the problem in all of these? The problem is scattered light. Scattered light here means that we don't just see the light appearing in our detector where it should be, namely the headlights are producing light that appears in our detector where the pupil of the driver and in analogy, the exoplanet is that we want to try to detect. Scattered light is a horrible problem. It's the limiting problem in all of these studies. And as you know, and we've talked about for this meeting, the brightness of the star compared to the integrated brightness of the exoplanet is a function of, well, these are all habitable zone exoplanets, and so as the star gets hotter, the planet gets closer to the star, and so the contrast goes down. The Earth around the sun is that number we've been talking about, which is sort of a part in 10 billion. The problem gets better as we go to cooler stars, and we now know that the universe is filled with interesting, probably water-bearing planets around fainter stars. And in fact, this number up here is 10 to the minus 7 rather than 10 to the minus 10. When we look at the thermal emission, it gets even better. So that thermal emission problem that I talked about, where we look for heat islands, thank you, is such that it would be doable with a contrast of probably 10 to the minus 6. I'm running out of time. The Keck telescope, this is the PSF of Keck, and we've taken away all of the atmosphere. This is a 10 to the minus 3 brightness scale. This is the wavefront of the Keck telescope. The diffraction associated with these highly segmented mirrors is a very serious problem. If we had an ideal telescope that performed with known coronagraphic capabilities, and we wanted to get to the signal to noise for Proxima B that I showed you with those inversions, we need a telescope signal to noise versus aperture, which is about 25 to 30 meters, if it solves the scattered light problem. When we look at a segmented telescope and we count the number of stars that we could see and we could do this problem with, as the number of mirror segments, that's what this corresponds to, increases, the number of candidates drops a lot. This is the telescope that we'd like to build, and the numbers are up here in the range of dozens. We talked about that yesterday. As we make segmented telescopes, that scattered light problem is horrible. The large coronagraphic exoplanet telescope, if you started with a blank piece of paper, would look like, I'm not going to go through this physics, but essentially we create the stiffness required to support the mirror, not with the mass of the mirror anymore, but with electroactive polymers. If we take a thin piece of glass and we use polymers where the energy density of the electric field, which is moving the polymer against the back surface of the glass, that energy density now matches the deformation energy and gravity of the system. And here's a picture of some of our tests. There's a group in Lyon, France that we are working with to do this. On the glass that we're using, it's a few microns, which is all we need. And these are things that we can print. So we put the glass in, this is window glass, we put it in the gantry and we print the EAP, and we end up with something that we can both polish and now support. Build a telescope in a different way. Make it essentially an interferometer, where each one of these is diffraction limited, and we combine the beams here. That means that we can synthesize the beam profile. This is what we call an Exo-life finder telescope. There's an odd number of mirror segments. Each one of those are as big as we can make it. This is a log scale PSF. It's not a filled aperture, but we can correct the light. We can synthesize a beam which has a hole where we want to look for the exoplanet, change the phases on the mirrors, and this is now the diffraction pattern of that telescope. It's like a physo-interferometer. It's like what the Texas people are doing with the binocular telescope, except now we have 19 elements. So we can achromatize the problem, we can have a large bandwidth, and we can move this dark hole around. The depth of that dark hole is more than 6 orders of magnitude. So that means we can begin to do the problem of finding the thermal light and the reflected light of very red exoplanets around other stars. We've fixed the scattered light problem before it gets into the secondary optics by creating a synthetic diffraction pattern which is optimized to match our needs to look for an exoplanet. That puts this telescope down here. It's got a much lower mass because we're using not the mass of the mirrors to produce the stiffness, but we're using the electrostatic energy of the polymer. This telescope is probably in the neighborhood of $50 to $100 million with window glass. The mirrors are never abrasively polished, and a structure which is a tensegrity structure, which is itself an optimal design to make it low mass. And I'm out of time, but these are my predictions for where we can be in 5 to 10 years. And the main one is I think we'll detect exo-life during our lifetimes using a ground-based telescope or an optical system like this one. So I'll quit here.
Do you have a similar graph of the actual running costs of large telescopes? Does it also follow? I mean, if you build a telescope for $1 billion and it costs $1 billion a year to run it, that's not great.
But I think there's a universal number, dimensionless number that says that the operation costs are always 10% of the building cost. And I'm sure that that's pure fiction, but we somehow make things work so that with 10% of the money, we find a way of operating the telescope. This telescope that we're describing is not any particularly, I don't think it's particularly more difficult to operate than, say, the GBT. And I could ask Ken or Jay, what's the operation cost of the GBT?
If you say 10%, you're not far off.
Okay, so that was sort of a soft answer, but I think that's right. I think that's right. In the bucket.
Okay, so I have 2 questions. So first of all, you showed at the very beginning, you motivated this with simulations of doing the inverse problem and being able to distinguish between oceans and continents. I noticed though that the angles that you used for that example are optimal. So for this, especially the latitudinal inverse problem. So I was wondering, how fine-tuned was that example to get the latitude?
I can give you our preprint where we go through all of the. It's not optimal to be 30 degrees. The worst situation is a rotation axis which is perpendicular to the orbital axis, as you might imagine. But anything else is actually fairly robust.
Okay.
So I honestly think that we didn't fine-tune that.
Okay.
We picked that angle because that's the Earth.
Okay, and then my second question is, given this design, wouldn't you want the mirrors to be able to move to create different baselines so you can get that hole?
No, it's not an interferometer in that sense. That hole, I rushed through it, but this structure right here does move. So it has the elements of a fixed pupil telescope with elements of an interferometer. That's a relatively floppy structure. Think of each one of those as essentially creating a different baseline by using the secondary mirror. So each one of these is its own telescope. There's a small secondary which does tilt the piston and does what essentially it has the dynamic range of what the trombones do in an interferometer.
We have time for one short question.
Does this design, has it been demonstrated in a smaller, I mean, obviously you'd like to see a prototype before you go creating this thing.
We're building on Haleakala a small version of this, which is about 2 meters across with fixed mirrors, we don't yet have the EAP non-polished mirrors. That's another step, but we think that we can demonstrate this over the next year. it's been demonstrated in the computer. Does that count?
Yeah. Let's thank Jeff again and all the speakers for the session.
And a quick announcement, those who are taking the shuttle tomorrow morning, please come and see me. We just want to make sure we have your name listed. After the coffee break, I'll read the results of the poll. When is that? In 15 minutes. Okay, if you please sit down, we'll get started. We've got Jill Tarter on the line here too, and she has a flash talk. I forgot to tell everybody what's happening next, which is I'm going to read the results of the poll, and these will be posted on the website in their complete detail with a Bayesian analysis. Also, then we have 4 more flash talks, and after that, Karen O'Neill, the director here, is going to talk about implications of this workshop for future events of this kind and try to get your input on it, and then we'll start the final panel discussion. First of all, because you could vote on the poll for more than one item, the numbers do not reflect the number of people that participated, but I can back that off. And there were fewer than 50% of people actually turned in a poll, from which I deduce that this is an audience of American voters. Within 10 years, the category that got the largest votes was no detection. But that was only a third of the votes. So 2/3 of the voters feel that there will be some sort of detection of life in the next 10 years. When you go out 25 years, in fact, I have the wrong sheet here. When you go out 25 years, it's reversed entirely. Almost everyone feels that there will be a detection by that time. And the leading candidate is around another star, a planet around another star. And there were a significant number that think through SETI. So anyway...
what was the percentage, Jack?
Of what?
For the 25 years, what was the percentage?
It was a third think that there will be detection on a planet around another star. And at that point, at the 25-year point, only 3 people think that there will be no detection. So it's a pretty optimistic group we have here. As I say, I'll put the results of the poll on the website for you to look at. We have 4 flash talks. Oh, one other announcement. Those of you who are around tonight are invited to a party at my house. As I say, we'll have a local fiddle, banjo player, and so on. And so just contact me if you need directions. We'll have some light snacks, and it'll start around 6:30, so you can get in to bed early. Flash talks.
Okay.
Yes.
Let's say...
Right, thank you.
Let's say at 2 o'clock this afternoon, I'm going to be taking some people... If anyone who hasn't left would like to see the control room upstairs, I will take some people around. And we're looking at taking some people around the 140 foot as well. So if you'd like to do that, please see me, and we'll try and get that sorted out this afternoon.
Yeah, and I promised a tour a little bit earlier than that, and I'll come through with that. Okay, whose slide is this?
This is me.
Oh, okay. I don't have my timer, so I'll just count mentally.
Do you want me to just, I can time.
Yeah, great, thank you.
Okay, so this is following up on what was reported on the first day. This is a slide that I showed in the middle of a conference and workshop on life detection that was held by the NASA and ESA planetary protection officers in 2012, addressing the problem of how to find extraterrestrial life. So we, as was recommended the other day, started out with our assumptions. We are looking for life that is based on carbon chemistry that happens at Mars-like temperature and pressure, so chemical conditions, physical conditions, and the thing that was missed the other day, on human detectable timescales. Timescale is very important, and on the basis of having a relatively short timescale, we indicated water as being the solute for that life. So under those assumptions, how do you find life? So in order to do that, we don't have a definition of life, but we do identify qualities that were considered as relevant to life. structure and morphology, both at the macroscopic scale as well as the microscopic scale, chemical composition, heterogeneity of the chemical composition, and then environmental and thermodynamic context. Where is it? What are the chemical surroundings of it? Okay.
Time.
Yeah. So, yeah, if I can take.
Thank you. Is Alicia Weinberger here? Would somebody take a look and see if she's out there? Because she submitted a slide, and I know she was here earlier.
She left.
Okay.
Oh, okay. Kelly.
Okay, so on this one, I'm actually trying to wear my biologist hat here. I think that if life arises on any kind of decent-sized planet, any decent habitable planet, it will almost always develop an extreme diversity of an ecosystem. So there are two implications of this. One, we don't really need to worry too much about definitions of life, despite the fact that I work on that, because I think that when we see it, it's going to be blindingly obvious. It's going to be a huge ecosystem. Maybe there's special cases like Mars, which is, to use the Princess Bride phrase, mostly dead, perhaps, but generally speaking, it's going to be pretty obvious. And then the second one is, in most cases, we should anticipate social and interactional life forms to evolve eventually, since life will explore all niches, and this is a very robust niche. So I didn't know the terminology, but I guess in Charlie's terminology, I'm a planet of the apists. Apists unite.
Thank you. And the third one is Jill. Are you online?
I am. Can you hear me?
Yes, you have 60 seconds starting now.
Okay, so I wanted to talk about Clarke's third law, and for those of you that don't know what it is, it's a small print. Their traditional values starting in 1970, Penny Boston calls our post-Cold War phase, which says that any sufficiently advanced technology is indistinguishable from magic, and that's what we've been doing. We've been looking for the Earth on asteroids, we've been looking for this magic. But more recently, in line with the kinds of things that David Grinspoon is talking about, Carl Schroeder suggested that that law should be that any sufficiently advanced technology is indistinguishable from nature, thinking about sustainability. But the thing that I didn't hear anything about in this meeting is what Nick Bostrom might have said. He has not said this, so I put quotes around his name. Is that any sufficiently advanced technology is indistinguishable from paperclip. And if you don't know Nick Bostrom's work, this is really saying that any super intelligent singleton that isn't well constrained, it doesn't have a good goal, turn everything into paperclips to be sold to build a million paperclips. And I think that what's been missing in this meeting is a discussion of this third possibility. What if what's out there and what we're looking for is not biological or is post-biological? What if it's Martin Rothblatt's mind files? How are we going to find that?
Okay, thank you. Are you going to stay on the line, Jill?
I am.
Okay, good. Let me introduce now Karen O'Neill, our director here, who just wants to get some ideas and kick some ideas around about how we might move from this workshop.
Thanks, guys. So, I just wanted to take advantage of those of you. First off, thanks to everybody that has hung it out. It's been fun. It's been busy. I certainly haven't gotten enough sleep, and I suspect that's how all of you guys feel. So I want to just say, from my perspective, certainly this has been a fantastic conference. We've had all sorts of great ideas coming out from astronomy and biology and chemistry and ethics and law and philosophy and pretty much engineering and almost everything in between there. And like all great conferences, I often end these and then we say, wow, that was absolutely fantastic. That was so much fun. And then we go home or go back to our office and get back to our job and we reminisce about it. But a lot of times, conferences kind of end at that point. And we'd like to take this farther. So we've already had a couple of great offers of publishing some of the results from this. So certainly, as we heard yesterday, the International Journal of Astrobiology and Rocco offered to publish within that. We've also had an offer from the American Philosophical Society's Transactions Journal to put together some of the results from this into one or a series of papers within that journal. So that's great, and we'll be sure to be working with you guys, following up, getting the information out about that. So that's one step, and that's a great way to get the information continuing to go, and as well as a lot of the really great ideas that have been discussed here out to our colleagues that couldn't make it, to keep that conversation going. But what I actually wanted to talk to you guys about a little bit, or mention and let you guys talk about actually, is the idea of these workshops and whether we all feel, everybody that's left, that there's a value in continuing these workshops, and there's a couple of ideas behind this. So one would be to say, maybe we all get together collectively, plus whomever we can gather in, once a year, once every few years, to just revisit these topics and talk about where we are, where we're going with them, and that's certainly, I think that has a lot of value. That's one of the possibilities. Another possibility on the table would be to get together and focus on some of the concepts that were discussed. There's a lot of ideas talked about in the last 3.5 days. Discuss some of these concepts and focus on those. Now, having said that, or we can combine the two ideas. Maybe we have some focused ones, and then every few years we get together. The one thing I wouldn't want to lose is there's a lot of workshops out there, and there's a lot of workshops on very specific topics. The goal of this particular workshop, and some of the ones we've had in the past, is really exactly what you see, this multidisciplinary idea. So when I talk about focusing on an area, I'm not saying let's go build the next mission. Maybe we talk about that mission and all of the implications, ethics, and everything else that are involved in it. So that's my thoughts. And rather than me saying, hey, this is what the next workshop should be on, frankly, I have no background in astrobiology except for all the workshops I go to. I'd like to hear from you guys and hear what you think would be valuable to do, and how we could continue this conversation within ourselves and within the community. So I'll stop talking and take any ideas or suggestions. Yeah.
So I'll say personally, this is my first astrobiology conference that I've been to. And coming into it as an astronomer, I had a completely different picture than what it's turned out to be. And I've been pleasantly surprised by how extremely interdisciplinary it is. So I personally wasn't expecting there to be anthropologists and philosophers and lawyers here. And I think that really enriched this whole dialogue. So I personally would be wary of trying to focus an astrobiology conference on a particular topic, because I think that will go against the rich interdisciplinary nature of these meetings.
Yeah.
I would like to second that comment. One of the great things about this workshop is that it's relatively small, and unlike a huge conference like AstroCon, where you may have anthropologists and philosophers and astronomers and geologists and biologists together, they frequently really don't have the opportunity to interact. But in a setting like this, with 50 invitees, we have all really interacted with one another. And everybody's got to experience the diverse viewpoints and the diverse subject matter that we need to integrate in astrobiology. So I would encourage you to stick with this format and revisit this every so often.
Back there.
Yeah, I love the revisiting, but let me clarify what maybe you're talking about, or maybe it's a compromise. And it's sort of like the blind man and the elephant. You can focus on the elephant with a bunch of different people, or the forest. And this is definitely a soup to nuts sort of conference that we've had the last few days. I could also imagine bringing all these disciplines to focus on a particular problem. And that would provide the interdisciplinarity, but give a little bit more focus to the meeting. Not that I didn't enjoy this immensely, I did, but I'm just trying to see a way to sort of split it up.
And the only reason, and hang on a second, the only reason that I'm suggesting both, I'm kind of agnostic which way we go, is that certainly I know within my field, there are times when you go to annual meetings and you're learning, you feel like you're rehashing 90% of what you talked about the year before. So that's the one bit I would like to avoid, is you got to rehash some. You can't not do any, but you want to make sure that real new discussions and real new progress is happening.
Yeah, so first,
Thanks for the interdisciplinary inclusion, much appreciated. On that subject of which way is the best way to do it, I wanted to kind of actually second what Lynn was saying, with appreciation for what you were saying. So yeah, if we chose a topic, and if you gave everybody sufficient advance notice, give us some lead time. Your social scientists, your humanists, your philosophers can all speak to a given topic. So let's say just we wanted to talk about exoplanets. From instrumentation, from literally kind of from the ground up to the sky, entire kind of processes of how different science projects are conceived, built within a larger social context, and then we also wanted to talk about, okay, so what's the societal effect of all the exoplanets that have been detected, and what will be the effect of when the big detections start coming in terms of indications of life. Like if we all focused around that question, a lot of different fields could be brought to bear on just that one subject, and ditto for multiple different areas. I think that one, could, for whatever it's worth, could be a really good one, because a lot in SETI has kind of been treaded over kind of repeatedly with some progress, others areas not so much progress, but anyway. But exoplanets, in terms of the societal significance, particularly the societal significance of a living world far away, I think that's been underexplored, and I think that would be tremendously fruitful. And I think from speaking with astronomers who work in this area, I know that there are some questions in the community about, well, how is this going to play out in the public? What is this going to mean for, say, how we relate to Earth? There's a lot of questions, and so I think that for whatever it's worth, I think could really be fruitful.
Yeah.
It's come up several times during the workshop that we feel that we're talking a little bit in an echo chamber, and no one's really going to listen to us. Well, I went to a workshop earlier this summer hosted by the American Institute of Physics that was specifically for historians of science. And the whole point of the workshop was just to gather in small groups of 3 or 4 people, and then talk about what you discussed over the course of an hour with a larger group at the end. And the whole point of that workshop was to write up a white paper on the results of the workshop. So I'm not saying we should write a white paper, but maybe having the format of small conversations leading to a larger group discussion and ending with some sort of tangible voice from the workshop that we can amplify might be a good idea moving forward.
I like the idea of focusing on specific questions while keeping things interdisciplinary, so I'd like to second Lynn's comment. And one reason why I like this is because we're seeing a convergence between exoplanets and planetary science and SETI, where exoplanet scientists are starting to increasingly think about biosignatures, and SETI scientists have always thought about technosignatures. So I think there's fruitful things we can do to take advantage of this increasing convergence, and see if we can, for example, figure out what types of technosignatures we might be able to detect with, I don't know, blue-born headaches, for example. So, which I don't think a lot of people have. Well, so there has been like a technosignatures report that recently came out, but I think that it deserves an actual broader workshop.
Yeah, back in the back.
What I'd like to say is that I think that even though this has been a very broad workshop, it's still one portion of what astrobiology actually entails. Astrobiology is actually even broader and bigger than this. The other thing I'd like to say is that, putting together a white paper I think is an excellent idea, because I've been in many workshops in which after the workshop ends, that's basically it. If you put together a white paper, you have something. But then I've also been in workshops where you put together the white paper and the white paper just sort of sits there. So what you have to do, I think, is put together a white paper. Then from that white paper, whichever discipline really is represented in that white paper, you have to go forth and publish it. And it has to be then promoted. Because there are publications that you say, okay, we've published it, but then it just dies. So it has to be promoted as well. In addition to that, one more thing, then I'm finished. And that is that the idea of taking one topic and then going at it from several different disciplines is the way that the first few ABSCICons were actually put together. on particular sessions within that conference. That worked really well because you got a broader understanding, people within a discipline got a broader understanding of one particular topic. Even if they studied that topic, they didn't appreciate all of the other ramifications. I think that is a great way to go. And that's all I have to say.
Yeah, I actually wanted to second what has
Karen,
been
this
said.
is Jill.
Hang on one second, Jill, we'll get to you right after. We've got somebody and then we'll get you, I promise.
Yeah, and basically what we know from team science, when you do hands-on work, is when you bring together interdisciplinary teams, it really helps focusing them if they have one concrete problem that they need to solve, and a roadmap for how to solve that broadly, leaving lots of room for creativity and bringing all different interdisciplinary points of view into the problem, and having a product at the end, whether it's a white paper, a presentation, a roadmap, or something. So,
Yes, Jill?
Yeah, I think there's an elephant in the room here. I think what we do next is determined by what we can afford to do next. Catherine Jennings alluded to the fact that this is not the first time that we've tried to have these cross-disciplinary, and it's not the first time that focus groups have been put together to try and go after a problem from a multidisciplinary point of view. But they've stalled, failed, gone nowhere when funding wasn't available to continue the activity. So I think really what's realistic in terms of what can we afford.
Yeah.
Yeah, I'd like to make 2 points. One, a suggestion for a topic, because this is something that I've been thinking about for a while, and that's eccentricity of orbits. Because that's something that could be taken all the way from the astronomical to the biological level. You know, what does that mean? Is there some limit that would preclude biological activity and so on? But the second thing is in terms of structure, and I'm as bad as the next person, if not worse, at following through writing papers. And it occurred to me with a small group, you could do a structure it so the first day you have, regular talks. And the second afternoon you've come with sort of white papers and you can start doing speed dating. So, I know that there's a gap in my knowledge on extrasolar planets or whatever. Hey, Alan, would you work with me? And so you form groups, and so you've got the second afternoon maybe to go off and write, and the third or the fourth afternoon to polish them off, and so that you're pretty much at a finished manuscript by the end. Because there's nothing like being in a wireless radio-free environment. Focus on writing.
Yes.
So, did AJI make a volunteer to publish proceedings of some kind, or the equivalent of proceedings?
I didn't say it. I don't publish proceedings necessarily unless they're individual research papers that can be peer reviewed. If they're individual research papers that can be peer reviewed, that's what I want to publish.
But not bound into something that you call
a special issue. If there are enough people who are interested, we can call it a special issue from this particular workshop. But proceedings, if you call them proceedings, they have a tendency to have a bad connotation because that means they're not necessarily peer-reviewed, they're not very long, and they're not in-depth. But peer-reviewed individual papers, if I can get a whole compendium of them together, we will have a special issue.
So the idea, and maybe this is going to happen, that we would have a place where all of the talks were recorded on the web publicly would be really nice, and I hope that happens.
That is happening. So actually, they're all being, not only are they all being recorded, but Jill is already starting to post them, the talks themselves, which isn't the same. I know it's hard to watch all the talks, isn't the same as the other pieces, but that at least is happening.
I know we have science writers here, but I mean, did you ever invite the press to come? Because twice a year at the AES, there's always a week where there's huge press releases and things, and the public get excited for a week, then they wait 6 months, and then there's another thing. But it would be great to see pictures in the local newspapers with, say, this was discussed. It would get the message out there, because white papers and everything else, we're really just preaching to the converted here. What we need to do is convert the preachers.
So I'd like to comment on Jill's point that these focused workshops, for them to be truly effective, they need funding to implement the ideas that come out of the workshop. One way around that could be if the question on which the workshop focuses uses existing or future instruments, which are presumably going to be well funded, hopefully. This also touches upon the point that Andrew Seaman made, that SETI isn't perceived at the same legitimacy level as other sciences at NASA. Maybe if there are enough workshops that try to tackle questions such as, can existing or future NASA instruments, would they be capable of doing for free some SETI science? And what types of observations or what type of SETI information we could extract from existing or future instruments and observations, then maybe that would both raise the legitimacy of SETI and it would avoid the need for funding to implement these ideas. So.
I spent a while talking to Fleming Krim about exactly this, and he felt, our discussion was a lot along the lines of, and this isn't SETI only. Somehow daytime TV just showed up on this, but so this isn't SETI only, but the idea that we need to find a way to get public to see the value in non-detections and in pushing limits, and that there's a huge value in continuing to push the limits down. Every SETI experiment has huge value because a non-detection is still telling us something. And so he, spent a lot of time, we were actually talking about nanograv and this and that and the other, but this whole concept of trying to find a way to get the public to see the value in non-detections, because there's a real value there. And we're all guilty of not always publishing our non-detections, but they tell you something, and they tell you a lot, frankly. The more you push it, the more interesting they become, personally. Yeah.
It might be helpful to invite also policymakers who can assist to, we've been talking a lot about ethics, for example, or possible dangers in how we are managing the planet and so on. So if there could be policymakers who could implement, perhaps, or help implementing these to a more concrete form, that would be perhaps helpful.
Any last thoughts on this? I have lots of ideas. This won't all go away, I promise you. That you'll start getting feedback on this. Taking all these ideas into account. I don't think we're going to solve exactly what we should do in a year's time right now, but I appreciate the thoughts. Any last ones before we can start?
Question just for so a lot of the presentations here are probably based on, I presume there's some white papers behind, like Jeff's, for instance, is the most recent, so it's easiest to think about. So I guess there's a white paper on your, and so does that get published also in the Astrobiological Journal too? So it seems like that would be an easy thing to publish in that topic.
I think if you want to encourage folks here to write real papers and submit them to AJI, you should set a deadline for when you feel like you could bundle them, realizing that they all have to be refereed, but there is something to be said for an event in a journal that advertises this ongoing biennial or whatever it is series of
We could certainly do that, and I would encourage everybody to do that. And so if there are sufficient numbers of papers, and I would say by sufficient, I think that maybe at least a half a dozen papers. Now, I've already talked to people here who said that they are going to write a paper. We have not talked about deadlines, but if we're going to really put together a special issue, then there does have to be certain deadlines so that we can get everything together and coordinated for a special issue. The other thing I'd like to say, just in case anybody's worried, there are no page charges, okay? Not even for color. Okay. So color is free. Page charges are free. If you want absolute free ultimate access, that costs. But other than that, everything, publication is free.
So it sounds to me like one of the follow-ups, and I'm going to stare at Jay as the primary organizer before I get to the other people, is that we should be reaching out to all of you and say who thinks they would like to write a paper, give us the topics, and act as that organizer to
If you could do
find
that.
out this information so that then we can decide if this is going to be a number of individual papers, which is great, or a coordinated series of papers. So we will put that onto our list of things to be done. Find out from you guys as you think about it, and see what level of organization we, means Jay, will do that.
I think that's a wonderful idea, and we should really talk about the coordination effort a little bit more.
Fantastic. I think there's a couple other things stated.
Karen, number one, I want to emphasize or reiterate what quite a few people here have said about the interdisciplinary nature of the session. I mean, obviously, it wasn't interdisciplinary, I wouldn't be here. So I'm all for interdisciplinary discussions, but beyond that, I have been just fascinated with listening to people from different disciplines talk about this subject. It's totally enriched the conference, as far as I'm concerned. I think the idea of doing these regularly makes a whole lot of sense. The second thing I wanted to say is that, you know, as I think back over the last 3 days, what my takeaway personally from this is that, you know, I had always seen the SETI as a search for intelligent life. And what I've learned in the past few days is that SETI is simply part of a much broader search. And that is a search for the origins of life, and to answer the question whether life in the universe emerged only here or elsewhere. Because not only was it mind-opening to me to think of it more broadly, but as many other people have said here better than I think if we articulate this effort in that broader sense, it's far more defensible, and also it avoids the problem of trying to explain why you haven't succeeded, because as long as you're engaged in the search for the origins of life and to try to answer this question, you're always successful. And I think it makes it much more publicly acceptable and interesting. And so my second point is, to the extent you can, in future conferences, reinforce that broader nature of the scope also, it would be very helpful.
So I like the idea that things get captured and published, but I want to point out that a lot of what I really enjoyed about this conference would not go into a published, paper in IJA after this, and that's because a lot of what I've heard that I enjoyed so much and has enriched my experience has been stuff that's maybe previously published, or just the basics of philosophy, stuff I haven't known that might not itself be publishable. So I think a big value of this is the value to the participants having been here, and I know exactly what you mean. But you go to the conference, you go home, and it's like you were never there or something. But I don't feel like this did that, and I think it's because of who came and what they spoke about and how enriching it was. And so I want to make sure that when we repeat this, we don't focus on an output.
Right.
Because so much of the value is not something you capture there. It's it's over drinks in the Drake Lounge and so on.
Thank you.
Well, if we put this together, when we first came here, it was not focused on an output.
Right.
The output actually, as an organized output, came actually right now. I mean, I just approached everybody individually.
And that's great.
With that, we do have to end this topic because we have one more panel discussion to go to keeping us all from lunch. So with that, I do not know who is in charge of this panel, but I will invite you to come up here. And, so thank you guys for your input. I really appreciate it.
Okay, I will get this started while the panelists are coming up. So we've been hearing about moonshots and earthshots for the last 2.5 days. Earthshots were defined as things that we might expect to develop or happen within, let's say, a decade, moonshots, things that might develop or happen, or goals that were multi-decade goals. So what I have asked each of the panelists, and we've got 5 people up here, but we're actually 6 panelists because one of our panelists is going to be representing another one of our panelists, and that is Catherine Denny representing Kenny Boston, and unfortunately Maxine can't be here. So what I have asked each of our panelists to do is to spend 5 minutes, and I'm going to time them pretty precisely. We've got an hour for this panel, and so each person will have 5 minutes. That'll take the first half of the hour, and then the second half of the hour will be open for discussion. I have asked each of our panelists to speak for 5 minutes on a goal or development or concept that they envision for astrobiology that would take a century or more to develop. So we are now shifting our horizon out 100 years. Now just for a second, put yourself 100 years ago and try to think about what people 100 years ago would have projected relative to today, and you immediately get an appreciation for the challenge of doing this. So what I'd like to do is I'd like to start at the far end of the table and work this way. So where are you guys sitting? That determines who's first.
Oh, we're just sort of winding up the talks right now, so
Okay,
you
but
tell us who's first.
No, you choose seats. Okay, Anna Maria.
It's fine. Yeah, I can go first. 100 years from now. My first postdoc, we had this forecasting project that was sponsored by IARPA, and we had to forecast science and technology. And I remember we had this very nice quote: "Prediction is extremely hard, and especially if it's about the future, right?" So, how do I envision astrobiology 100 years from now? I think we live now in a kind of a Babel tower of sciences where there are different sciences, and 100 years from now we will have just one science. And so kind of like Star Trek, you have the science officer, it doesn't have a specific science that is associated with that. So that's how I envision astrobiology is going to, since it's so interdisciplinary, that is going to encompass all the sciences, and it will be just one science. On the other hand, I do think that our biologies will evolve, and in order for us to explore more, we will also have interfaces with artificial intelligence, and we will have more artificial intelligence type of algorithms that will come into play, that will help us discover more, that will help us think through critical problems. But we will also have advances in biotechnologies that will help our biologies, that we will become more enhanced, involved human beings, and thus it will help us actually think differently about how we will connect with, or how we will search for life on other planets. And let's not forget that there are huge strides that are being made now in DNA computing, and this means that instead of zeros and ones, maybe we'll have genetic codes that we will use for storing data, for transmitting data, for communication. And I think, again, there will be a hybrid between the type of artificial intelligence and biocomputing that will help us think through the problems, through the scientific problems 100 years from now. And maybe that's actually how we will eventually discover and connect. And one more slight note that I'd like to make here. In the forecasting community today, there are different ways through which we are trying to predict and use predictions and forecasting, whether we are using machine learning, deep learning algorithms, but there is also something called the wisdom of the crowds. And we had experiments through which we compared the wisdom of the crowds with the theoretical models and with the statistical laws that we know now. And they were on par. So the models, the theories, the models that we know right now, they are no better than the wisdom of the crowds when it comes to predicting science Science and Technology. And I'd like to mention this platform called TESS at George Washington University that has been running very long-term predictions for a very long time. It's 30 years old now. And it's based on expert and on expert opinion. And one of the questions that they have there is, when will contact happen? And it has been consistently forecasted around the year 2060. That's my take on it.
Thank you very much, and thank you for keeping right in time. How about backtracking to Lynn?
Okay. I'm going to go up and run the slides. Is it possible to turn the lights down? See, the beauty is then Carl can't see the clock. Okay, so Carl asked us to look 100 years into the future. So I thought that what I'd do is sort of start you with the way I usually start talks when I'm doing the whole life in the universe bit, and then try to fast forward. And so I would argue that since the dawn of humans, we've wondered if we are alone, that this is probably the oldest human question after how do you make babies and what's for dinner. But this is the first time in history that we've been able to approach this question scientifically. So how do we do this? Well, we start with the Earth and ask if it could happen again, where, and how would we know? But I would argue that this is the first time that we can do this scientifically, and there are 5 reasons for this. First is space missions. And so then I ask myself, we know where we are today in space missions, we know where we think we're going to be in the next 10 or 20 years. Where are we going to be in 100 years? And I've been told by the Science Technology Mission Director at NASA headquarters I'm coming to the wrong conclusion, but I firmly believe that a lot of it has to do with propulsion. How many people here want to spend 2.5 years of your life doing a round trip to Mars? How many people would do it if I said you could be back by next Thursday? So to me, that's the answer. It's all about propulsion. A lot of your issues of the human physiology go away, the human infrastructure, and so on. I am already on record of saying that the Apollo astronauts could have packed peanut butter sandwiches, but you just cannot pack enough peanut butter sandwiches for 2.5 years. So I think that that's going to be critical, and if we can solve the propulsion problem, we will have the missions elsewhere, and that will also speak to the extrasolar planets. Life in extreme environments, we have a very good handle now, far better than we thought that we'd have when I was in grad school in terms of where life can live. And I think it'll be even further then. We certainly, it is hard to believe that it's only been a few decades since Tom Brock published a paper in Science in the 70s talking about life in extreme environments in Yellowstone, the idea of life at 70 or so, and we now know of life confirmed to about 121, 122, I don't quibble. So, I think that we'll be able to know much more about the diversity of life all over, field trip money willing. We know so much more about molecular evolution. A couple of decades ago when I was in grad school, we'd sit around staring at micrographs, like they were tea leaves, and at the end of a long evening of arguing the importance of subcortical alveoli or, the 9+2 structure versus 9+0 in flagella, you'd say, oh, well, I still think I'm right and you're wrong, but of course we will never know. And the molecular biology has taken us to the point that we know so much more. I believe that we will know completely what all this so-called junk DNA is about, non-coding DNA, and therefore we will have the power to write whole new genomes. And by the way, using non-canonical bases and so on, which brings up the last point that I wanted to spend the last minute on, is, as I've mentioned before, I've been heavily involved in synthetic biology the last 12 years or so. And that is actually the first place that it's shown up in a NASA document was with astrobiology. And I firmly believe there are a couple of ways that synthetic biology is going to change everything, because in astrobiology it will not only enable the human missions, but more to the point for us, it's an engineering discipline, so it allows us to look at the art of the possible. We're only in science able to see what's actually happened. We're not able to do beyond a thought experiment, what would have happened if we'd had a 6-letter code? What if it had been in xenonucleic acid and so on? These examples are things that people are working on right now. And so I firmly believe we will find alien life in one of our labs in the next few years, not even 100 years out. So it's very difficult for me to predict 100 years because these fields are moving so fast. But again, it will give us the art of the possible. And so almost anything you'll be able to imagine. What if we had a life form that does X, Y, Z? Could you have life in 2 dimensions? Can you have life in a gaseous phase? We're going to be able to test all those things in our labs in the next 100 years. Thank you.
Catherine, do you want to be
I'll
first?
be Penny first.
You'll be Penny first. Okay, so this is Penny Boston, AKA in this case, Catherine Penny.
I didn't know that, well, first of all, actually, it's too bad as well that Steve couldn't be here. So the reason that I am being Catherine later is because Steve couldn't be here to be Steve. And then, and my task of being Penny was just given to me very recently. So.
But you don't have to be Steve, you're allowed to be Catherine.
Yeah, I'm just feeling guilty for having so much airtime. Yeah, I can't run computers. Did I mention that? Okay, great. Okay, all right. So yes, trying to be Penny as best as I can. So Penny actually addressed the question, which is great. I can't promise that I'm going to do the same thing. Multi-generational enterprise model. So just this idea of, so for century scale endeavors, and again, I think, we're agreed that astrobiology it's a long-term project one way or another. How do we actually maintain the interest, enthusiasm, progress, and also the resources for endeavors on this kind of scale of time? And so Penny was kind of thinking about different models that exist. Of course, there's always religions. When you have sort of a core ideology that kind of drives you and focuses your attention, that can maintain queries over a lengthy period of time. Some monasteries, for example, are extremely long-lived. One thing that's kind of interesting is how these different things dance together, though, because I remember at the 100-year Starship meeting, this is me, not Penny, but anyway, it's just speaking to her point, people were talking about the Catholic Church as a great example of an extremely long-lived institution, but they were speaking about it as though strictly a church. It's also a corporation, and it was also at one stage more or less, a government as well. So kind of disentangling these things can be quite difficult. The idea of very long-lived institutions, which are kind of perhaps governmental in origin, so museums, universities, etc., some of them quite independent. Again, some of those have lasted for extremely long times, rather longer than NASA, for example. And then she talks about miniature trees living for hundreds of years, which have been actually maintained by humans in bonsai form. So that kind of I guess kind of a multi-species interaction. So it's just kind of thinking about how we maintain questions on century timescales. And I know that, for example, Jill has done a lot of thinking about this as well. But so the other thing that Penny was thinking about was just this prediction of increasing fluidity between quote-unquote disciplines. And she's citing the increasing connectivity between our modes of information handling, which I think is more or less self-explanatory. But then she asked this great question, would Leonardo da Vinci make a good astrobiologist? And her answer is yes, because what a synthetic mind bringing together so many different things, but that he would actually never get funded under our current way of funding science. So she notes the principles for the development of a complete mind: study the science of art, study the art of science, develop your senses, especially learn how to see, and realize that everything connects to everything else. And I guess the question then is, how do you integrate this kind of way of thinking within structures that may not support that? So that perhaps is the tension or the question that Penny was driving towards.
Thank you, Catherine. And now, Catherine Penny.
Oh, can David go in between?
Okay, sure. Of course. Sure. David?
Yeah. 100 years from now, it's hard for me to consider where we'll be in astrobiology and SETI without thinking about where we'll be with managing ourselves here on Earth. They're obviously coupled, and especially right now, I feel like we're at some inflection points. And it's funny, I wrote this book, Earth in Human Hands, and a lot of people, and I've gone around and given talks stuff, and a lot of people accuse me of being an optimist. And that pisses some people off. Some people, optimism makes them really mad. But then I say, have you read my book? It doesn't don't feel like, because what I actually say is that the next century is going to be really, really difficult. There's going to be a lot of unnecessary pain and suffering and death because of the way we handle ourselves, but that we'll get through it, and there will be a 22nd and a 23rd century, and we'll have figured some things out the hard way. Does that sound optimistic? Well, maybe, but you know, we are at an inflection point right now. I feel, and I'm sure the historians will here will tell me, oh, look, you know, prospective people have always thought that, but both in terms of, and maybe we're not supposed to talk about this, but there's, you know, the future of democracy and public policy being made with science and evidence and expert knowledge being incorporated is under threat. Not just in this country, but what happens in this country, of course, is so important because of climate change, which is one of our biggest threats, but to me is just sort of indicative of a larger set of threats, of the need to be able to conduct ourselves globally in such a way that is equal to our power to change the world globally. So anyways, I do feel like we're at this pivotal time, and I'm not sure how it's going to come out, so I'm maybe feeling a little bit less optimistic than when I wrote that book a couple of years ago. But at the same time, I guess I still have the same overall picture that we'll get through this century, and that 100 years from now we will be post-fossil fuel, our population will have peaked and will be declining, we'll be repairing a lot of damage that we're going to cause by making these transitions too slowly, and we'll have learned some things the hard way. You know, Carl mentioned, you know, that it's interesting to consider predictions of now from 100 years ago, and I actually did a project that I called A Brief History of the Future, where I read a lot of predictions of now from the past. And of course, the one thing you do learn is, like, nobody can predict 100 years from now, and it's because, and a lot of smart people got a lot of things right, but it's the game changers we can't anticipate. And some of the kinds of things that Anna Maria mentioned about, you know, nobody knows what's going to happen with AI and how that's going to affect our future. A lot of smart people have a lot of ideas, but I don't take any of them that seriously, other than to just realize that it's going to change things in some unpredictable way. So, so the future on Earth, to me, matters for this because for a couple of reasons. One, we're going to be doing the experiment of, can a global technological civilization achieve some kind of a long-term reasonable accommodation with the functioning of a habitable planet. And that is an experiment that I personally believe in some form or another is probably being played, or has been played, or will be played out elsewhere. And I think that actually relates to how we think about techno-signatures, and will slowly inform us if we don't find a signal, which nobody can predict, and I fully support the search, then we can, as we look for biosignatures, as has been mentioned, we can look more and more for techno-signatures, and I think we'll get better at thinking about what a planet with a sustainable civilization might look like. I think 100 years from now we'll know if there's life in our solar system or not. You can't prove a negative, but I predict no life on Mars because I'm a Gaian, but which makes some of our ethical choices easier, but I fully support being really cautious because I could be wrong, and because it's a test of the Gaian idea that you can't have a little bit of life on an otherwise dead planet. I welcome that test, but I think we'll have, 100 years from now, we'll have a sense of having explored most of these places. We'll know, and if I had to predict, I would say we will know about other inhabited exoplanets, and that's going to be really exciting. Astrobiology will have become a comparative science in a way that it is not now.
Thank you, David. Catherine?
Thanks. I often start by saying my job as an anthropologist is to talk about cultural things and make cultural observations. They're not necessarily the observations that you might have in mind, however. So I'm going to have a hard time sticking very strictly to the question. I just wanted to speak briefly about a couple of different things. First of all, the idea that since the dawn of time we've wondered, are we alone? This is a common notion in this community. I would actually dispute it almost completely. I would say that since kind of the dawn of humanity, actually, we've been quite sure that we're not alone because the we has been defined differently. So it's not in the strict sense of, you know, life on other planets, but the universe has been very lively for humans typically. It actually just kind of emptied out and got very quiet with the dawn of modern science and the dawn of modern astronomy. But, you know, we've spoken even in this meeting about, you know, how people were absolutely confident that Mars had life, and it was only once, you know, through the cold, hard gaze of the telescopes, it's like, oh, actually, no canals, thank you. So actually, you know, even just the duration for which Mars has been considered to be, yeah, maybe dead, probably dead, who can say for sure, but that's very recent. And just more broadly speaking, most cosmologies throughout time, I would say, have actually not considered this to be a question. The assumption is that humanity is not alone in any meaningful sense. And I want to flag that because I think those cosmologies matter too. They still very much exist. And these different things are starting to cross and to dance together. So when detections of life come, whatever form they come in, they're going to intersect with these already existing, still existing belief systems, which are quite different. And I think that it would be very wise for scientists to kind of prepare themselves for that for many people the heavens are not empty and actually never have been. So there's that. On the subject of futures forecasting and things like that, I tend to ascribe a little bit more to the backcasting model, which is that you choose a point that you want to be at and then you do your damnedest to make it happen. So the future is something that is made, not just kind of something that unfolds. So it does depend very much on all the choices that we make. There are a couple of kind of crucial things I think that can be said about collapse and about what happens to civilizations when they kind of overstretch, overreach, reach points of non-sustainability. It's commonly thought, because of various popular publications, that collapse tends to be quite complete and total. It tends not to be. It's usually kind of a rational downshifting in complexity, and then from there you build back up again. So you lose some things, but it's not necessarily the case that everybody dies and it's total doom. So I think we have to expect a continuation of certain trends that we are seeing. Some things are collapsing. It's not completely in the future. It is occurring. But equally, there is rebuilding. There is creative adaptation, and of course, there has to be a lot more of that. I just wanted to say just a couple of things just very briefly about the interdisciplinarity aspect here. Since some of this is hard, some of the conversations that we're trying to have here are hard. Working across disciplines can be hard in and of itself. So I'm gonna have to try, and also technology is hard for some of us. Where is it? I can't drive Lynn's computer. So I'm just looking for panel, sorry. Yeah, oh, right, okay, great, thanks very much. Just super quick, a couple of things that I just wanted to sort of, in a sense, clear up, because I do think one of the things that we're all going to need kind of going forward is better ways of integrating social sciences and humanities into large scientific conversations. And I think the NASA Astrobiology Institute was a shining example of this. One of the reasons that it worked is how carefully it was designed from the beginning to enhance collaboration. And a lot of social science went into that thinking. But anyway, here are just a few thoughts kind of going forward. We're also at a moment where technosignatures is really trying to integrate properly within astrobiology, but then there are some kind of consequences to that in terms of, thanks. I need all the help I can get. One more, all right, great, thanks. So I do think we need to be thinking very concretely about planetary protection. And I would actually say that even if it's outside your wheelhouse as an astronomer, if you want to be part of astrobiology, you have to be part of that conversation. There are also some really concrete things to think about in terms of future uses of the solar system. Don't listen to the anthropologist, listen to the astronomer who did the actual calculations, suggesting that unless we leave a significant proportion of the solar system wild, we are going to be in trouble. I also wanted just to say that very often what's happening when social scientists and humanists are kind of telling you things, we're actually relaying stuff that emanated from within your own community. So we're frequently reiterating ideas that kind of actually came out of scientific community. So for example, the idea that we need to be looking at potential impacts of detection, that wasn't hatched in my office. That was hatched at NASA Ames by scientists. And I'm just kind of continuing on that tradition. Also, really important thing, am I totally out of time? Okay.
Finish your lesson.
All right, finish this one. We are at times also reflecting back to things that we've heard from within your own scientific community, from those who don't feel able to speak. I just want to flag how important that is. So whether it's your workplace or different power structures, et cetera, sometimes we are, voicing things that are not just our opinion. We've heard them from you, and we're just trying to put it back in front of the community in a safe way. So, edges of scientific responsibility, we're not going to agree. But it's a good idea to consider extending your circle of concern and care as much as you can. One more thing, multiple stakeholder problems are hard. The future is full of them. Scientists are not going to be able to stay out of these anymore. Sometimes we've been able to work in kind of small, tight bubbles. Those times are over. So it's going to be kind of continual negotiation with really difficult situations. And I think the good news is there's a lot of experience out there in the world about how to do these things well. There's better ways, there's worse ways. We can all learn, and I think that will help us get through the next century.
Thank you, Catherine. Okay, I will finish up and start my stopwatch. Okay, I'm going to start off with two assumptions. I'm going to assume that SETI is both science and engineering. There may be people in this room who disagree with that. I doubt it, frankly, but that's one of my assumptions. Another one is that biology creates technology, and even if we're talking about post-biological technology, it started with biology, so that just pushes the problem back. So given those two assumptions, I would argue that there's no more compelling a scientific question raised by SETI than the nature of the biology that creates the technology that produces the technosignatures. So you could say, nah, let's detect it first and then we'll worry about the source. But I think that ducks the real challenge. Considering the possibilities for life as we don't know it is part and parcel of astrobiology, and if SETI is a part of astrobiology, which I believe it is, then considering the possibilities for the source of the technosignature, I think, is implicitly a part of SETI, and the SETI community rightly should be considering that. So SETI posits that creators of technology that produces technosignatures are intelligent, but I would ask the question, what else might we ask or conjecture about those creators of the technology? And to me, the most profound question is, are they conscious? Now, some of you may remember the flash talk that I gave. I defined intelligence and consciousness in two straightforward but ultimately complex ways. Intelligence is the ability to solve novel problems in a changing environment, and consciousness, and particularly what Chalmers called the hard problem of consciousness, is the state of having an experience, the state of inner subjectivity. It is a state rather than a function. There are many functions of consciousness, and we study those functions. But the hard problem of consciousness, the essence of consciousness, is this state of experience. So there are at least two ways that I can think to argue that the creators of the technology are conscious. One is that biology that creates technology, given that the technology is something that's external to the biology, they're creating something that performs like a radar, that performs like a laser, likely has three things. One is an internal model of self. The second thing is an internal model of the technology. And the third thing is an internal model of the relationship between the two, which you can think of as a model of attention. I'm looking at this speaker in front of me. I am attending to this speaker. In order to do that, I have to have an internal model of me, this speaker, and the relationship between us. Those three properties are what are ascribed as producing consciousness in a theory called the attention schema theory, which was developed by Michael Graziano at Princeton and colleagues. And so the argument in AST is that you put those three things together and you get consciousness. The second argument that I would make is that the creation of technology probably requires culture, and I'd love to hear Catherine talk about this, and implicitly cultural evolution. And that cultural evolution probably requires consciousness. If that's correct, consciousness may be much more common in the universe than technology, because you can easily imagine, in that case, consciousness that doesn't produce technology, and I would just suggest on Earth cetacean consciousness and feline consciousness, just for example, didn't produce technology. So, so that raises the question about whether consciousness is a convergent property of evolution. Now, I am not trained as a biologist, and I'm going to avoid practicing evolutionary biology without a license. But I would argue that there are at least two instantiations of consciousness on Earth. One is in the vertebrates, and one is in the invertebrates. Now, in the vertebrates, you can make arguments from both brain structure and behavioral studies that all mammals have some degree of consciousness. You can also make the argument that many birds show evidence of consciousness. Whether this is one evolutionary example of consciousness or two is something that I don't feel qualified to get into. But I would assert that in the vertebrates, you at least have one example of consciousness. In the invertebrates, you of course have the cephalopods, and the octopi or octopuses, depending on your preferred plural, is the primary example. And if you question whether octopuses are conscious, I recommend Peter Godfrey Smith's book on the subject. It is a wonderful, wonderful read. But I would submit that octopuses show evidence of consciousness. I would also note that pain and suffering, which Lynn yesterday offered as a standard for making moral judgments, do not exist in the absence of consciousness. Pain and suffering are experiences. So, NASA has a definition of astrobiology. The definition is the study of the origins, evolution, and distribution of life in the universe. My proposal for a 100-year goal is to make major progress in understanding the origins, evolution, and distribution of consciousness in the universe. Okay, we are now open for general discussion. Let's start with Jason.
I've got a lot of thoughts about what you said. That was really interesting. I want to offer not a rebuttal, but a thought experiment to muddy your lines a little bit. Sometimes we talk about, beavers as great engineers, and they build these technologies, and they don't do it they don't approach that engineering problem the way that would approach that engineering problem. So they're producing technology in a different way. Now, that doesn't get to your conscious thing, because we presume beavers have a level of consciousness. But let me propose a way that SETI could stumble across non-intelligent life. So let's say we're looking for waste heat, and we find what's just got to be a Dyson sphere. It's large structures in space blocking the light, and somehow we manage to study it well. And we just never see radio signals, or maybe we do see radio signals. And what it turns out to be is space trees. That these are biological structures on very large scales, using photosynthesis and collecting material that comes near them to just be gigantic trees in space, and without gravity they can grow quite large. And we know that trees, have ways on Earth of interacting with each other with particles. Perhaps it's radio waves that they use to do something similar. So here we have a completely, the best analog would be trees and plants. So we have no sense of consciousness, we have no sense of engineering, and yet this is totally something we might pick up with radio waves and waste heat. So I offer that just to blur it up a bit.
Thank you very much. Can I make a quick
Sure.
Trees have consciousness. There have been some recent papers about this. And if trees on Earth have very primitive neural communication systems, imagine how evolved space trees might be. Who's to say? No, seriously. I don't think you can make that assumption.
I'm sorry. So my thought experiment was to muddy things. No, okay. Point taken. Imagine non-conscious trees.
We have the space beavers and the space trees. How does that go?
Hi. Synthetic biology is both exciting and real. I want to ask you to tell us a bit more about the progress, for example, in 6-letter genetic code.
So there are a couple of people who've been working on that sort of thing. Steve Benner mostly has been working on the 6-letter code, but there are a couple of other groups. And then there's a group, Phil Holliger at Cambridge, and now his student Vito Pinheiro is now are all working on these XNAs. So what they're doing is trying to incorporate them into strands of canonical DNA using some of the normal enzymes to try to transcribe them into RNA and reverse transcribe and so on. And to me, what's fascinating is talking to someone like Vitor, who is a far better chemist than certainly I will ever be, and I'll say, okay, look, my problem is you've got life evolving on a planet with a high UV dose, and these organic compounds all absorb in the UV. Can you make us something that at least is a little bit less dangerous? And he says, well, yeah, we'll just get rid of this double bond there, and we'll add one there, and next thing you know, you've got an alphabet that's just a little bit more resistant. And so it's that kind of thing that's fascinating. What I've been thinking actually ever since I left this meeting last week is it would be fascinating for them to try to make a genetic code with the bases that are normally found on meteorites. Right. I don't think anyone's actually done that because, unlike this field, synthetic biology's got a lot of money, but it's for the applications, the drugs, DARPA, all that sort of stuff. So there's less money available to play for the astrobiological significance. I work for NASA. I've taken a vow of poverty, whatever.
Okay, Russ.
So I really like the theory of consciousness you described, and I think that to me the key concept there is recursion, which is you inside yourself you have a model of the universe that includes yourself in it, and I think that's the key element that leads to complexity of life. So I'm trying to think. Okay, so what is the signature of consciousness? You said we should be looking for consciousness, but as a, from an observational point of view, what is it that you measure? And I think that, and I'd like to know what you think about that, but let me offer a conjecture, which is that anytime you have complexity, that you measure complexity that you cannot reduce to a physics model, and that's indicative of consciousness, perhaps, or, because we tend to have these types of systems, whenever you have recursion in your model, you tend to get really high complexity. So should we be looking for anything that is, should we open our search to find things that we cannot reduce to physics models, and would that be consciousness?
I'm not going to try to answer your question, but it's a great question. I'm going to call on Jen and then Jeff.
I'm going to answer your question. Not really. There's no neuroscientists in the room, right? There's a lot of biologists. Yes. But they would know exactly how to answer your question, because we look for consciousness in other Earth organisms all the time. There's a huge research program on that, and there are techniques that you use to do that, among which are you assume that if an organism is conscious, that organism will use that consciousness in ways that are useful to it. And so you can set up tests for that. So that may not be the problem.
How about ET?
I can offer an answer from the artificial intelligence perspective. The field of artificial intelligence has struggled for a long time to put boundaries, Turing test, and that kind of things. What exactly is a computer, and when does the computer transcends to a place that, let's say, it's more like us, right? And I think it has to do with information and with the way we are dealing with information entropy. So in living systems versus in non-living systems, there are different ways in which information is being processed, is being produced, and is being consumed. So I think those can be potential signatures for how you can find consciousness versus non-consciousness in a broad sense.
Thank you. Jeff and then Kathy.
So nature is really good at solving problems and finding efficient solutions. And I go back to Jill's comment, which was Arthur Clarke's comment, which is any sufficiently advanced civilization is indistinguishable from nature. And I think what we're saying, if we think we're going to find a biosignature for consciousness, is that if it's sufficiently advanced, it's going to look a lot like nature. So I think there's an inherent assumption that we're looking for something which is closer to the Earth-like understanding of what advanced civilization is, rather than the far advanced civilization that would be so efficient and so much like nature.
Cassie?
Right, so I just wanted to say that it's very important to define your terms. If you want to say consciousness, if you want to say pain, and if you want to say suffering, you have to be very careful that when you're talking to other people, you all mean the same thing. The paper on plant consciousness was indicating that plants respond to their environment, they respond to injury. You can tell that the plant as a biological organism is responding to an external stimulus. That is very different than what neurologists consider to be consciousness.
Yeah, sentience might be a better word.
And I would very strongly dispute, plants are not sentient. The plants are sentient. They respond to environmental conditions. They are not conscious in the sense of having these experiences.
Yeah, just really quickly, my point to Jason was that if we have sentient plants on Earth, we could imagine that space trees would have evolved consciousness without breaking some category.
But responding to the environment is something that all evolved creatures have to do because they have to adapt. But pain is a neural response. Suffering is something that happens arguably in the mind, if you want to use that definition. But it's very important when having these conversations to have confidence that everybody is talking about the same thing. And I don't think we're here, given that I just heard it.
And biologically embodied cognition is the term that has been suggested to be used for the way plants interact with their environment. That article, if we're talking about the same one, was entitled Plant Intelligence, not Plant Consciousness.
Well, again, cognition and intelligence, you have to be very careful. I would argue that producing a chemical signal in response to a stimulus is neither intelligence, nor consciousness, nor cognition.
Okay, interesting discussion we could have there.
I was just wondering whether anybody has determined when a human fetus becomes conscious as opposed to life. I know that's a very provocative statement, but people are obviously going to have to struggle with this with regards to abortion issues and all the rest of it.
I would just be provocative beyond that. We sometimes ask, can you have intelligence without consciousness? And I think most people would say, sure you can. AI people envision intelligence without consciousness all the time. A perhaps more interesting and in some ways more limited question is, can you have consciousness without intelligence? Now, using the definition of intelligence as being able to solve novel problems in a changing environment, a fetus prior to birth may be an example of consciousness without intelligence. And you may have consciousness without intelligence, not for an organism's entire lifetime, but during different parts of an organism's life cycle.
Oh, go ahead.
Jill, did you want to say something?
Well, I just made a comment about flower sleeping, but I do have a question for Lynn when you get to it.
Hi.
Well, Lynn just wanted to make a comment, so how about Lynn makes her comment, and then Jill, you ask Lynn the question that you want to ask her.
Okay. I feel like there's been a total absence in this discussion of consciousness and intelligence today, Charlie's talk and so on, about the role of natural selection. If there's no selection for intelligence, you don't get it. You don't just sort of, some creatures may be more intelligent than others, but if you're selecting for speed or whatever, so what? It goes by the wayside. And my understanding is this is still sort of the best model that we have, is that we're intelligent because we came down from the trees and we were great prey and everything else, and we just didn't have time to evolve the speed or the sensory capabilities. Our superpower was intelligence for dealing with a highly variable environment. And if you don't have an environment that encourages it, and I would suggest that floating trees around a planet don't have a good selective reason to be intelligent, you're not going to get it. You may have the odd organism that is more intelligent than another, but they're not going to be selected for. It's going to come out in the wash in evolution. And I wanted to point that out because I think that's something that's been sort of an underlying misconception over the last few days. Jill, please.
Jill, please ask Lynn your question.
I feel better now.
Yeah. So, Lynn, I've said for a long time that the only way we're going to be able to figure out what is necessary, what is contingent life, is to find a second genesis. Synthetic biology people have been arguing with me and saying, no, we can figure that out. And my question is synthetic biology done in a way that we don't put our human life development biases into the questions that we're asking?
Are you talking about specifically origin of life research?
Well, no, all synthetic biology in general.
Okay, well, so,
Can you please
yeah,
repeat what I
okay, so
think?
that's,
Yeah,
that's
so-
the build-a-cell sort of thing, and actually, I'm part of the.
Let's repeat the question.
Let me repeat the question. So Jill asked that she thinks that the only way to determine the difference between what's necessary and what's contingent for life is to find a second genesis. And she asked Lynn whether synthetic biologists claim that they can do it without finding a second genesis. They can figure out what's contingent and what isn't. And Jill is asking Lynn whether synthetic biology is being conducted in a way so as to accomplish that.
Okay, there's a group that I'm part of the advisory committee called Build-A-Cell, and we meet twice a year. And these are people primarily in the United States who are interested in these questions. And I know the Dutch have gotten an awful lot of money to look at these questions. And except for Kate Adamala and me, of course, I would say that no one else is really fundamentally interested in the origin of life questions. The question, what can this be, what's the use for pharmaceuticals, drug delivery, that kind of thing. But there are at least two of us who go to those meetings who are on the advisory committee who are interested in that relationship. And I would submit that it's a matter of where the money's coming from. There's at least some interest in using it to look at the art of the possible. And I would emphasize that I don't believe for one moment there was one origin of life. There were probably multiple efforts. There was a lot of gene promiscuity and so on that was eventually hardened and something won out through a bottleneck. And so we can come up with origin of life in the lab, we can evolve it, but that doesn't mean that's the way it happened here on the Earth. But it harkens back to my comments that it does give you an idea of the art of the possible. What if under anaerobic conditions we start with pyrite and add this metal and can we do it? So I would say that's where we are right now, Jill.
Thank you.
You're welcome.
Other questions or comments from the audience? Yeah, Jim.
Going back to something earlier, I sort of wanted to amplify something that Catherine brought up about, when we as sort of humanities and social science people sort of bring things to your attention, I think she's right that a lot of it can come from the disciplines. But I think it's also valuable to keep in mind that, when all of us from these other areas seem to converge on certain things being problems that need to be considered, you should also keep in mind that maybe we have insight into this stuff that sort of trained empirical scientists wouldn't, and so to sort of recognize that there are sort of other valued forms of expertise, that outside perspective. I think Kelly and I were talking about this, how there's a certain objectivity that we can have when we're not so close to the details, when we're not so concerned about this particular research program, and so to just keep in mind that there's value to listening there. Whether the origin of the concern is from another person in the discipline or not, but I do really think Catherine's point earlier is a very important one we should not forget about.
Please.
Yeah. I was also wondering, Catherine, if you could talk a little bit more about expanding your circle of care comment, and like what you were envisioning as how that will influence the next 100 years of activity in this area.
Sure, yeah. So just to go back to this kind of question of, where does the responsibility of either the individual scientist or a scientific program kind of end, right? What is your business and what isn't your business, right? And so there's always going to be a lot of different perspectives on that. Like I said, we're not all going to agree because the reason for the differences in perspectives, it comes partly from politics, it comes partly from faith, it comes partly from personality and personal history in terms of what you think is your job to try to help with, or what you should just kind of let fly, and it's not your problem. So I guess what I've been seeing is, so a lot of this is kind of distilling private conversations, but if you recognize yourself, you weren't the only one. So in all of this. So some people, they're in a great deal of pain about kind of the condition of the Earth, our shared future, and they consider it all to be their responsibility, and therefore they're kind of, in a lot of pain and kind of burning out, frankly, emotionally from the wear and tear of trying to deal with the realities, and also that their concern exceeds their individual power is a source of considerable difficulty. So there's that kind of constellation, and that's very strong within the astrobiology community. So one of the things I find is that when I kind of stick my head up and kind of make a point about this, all the conversations that then come to me, and it's like people who are very concerned about these same things and haven't been able to articulate them in an open science meeting or something like that, or sometimes they start to. So there's that constellation. Then there's the others who draw kind of a much tighter line about, well, I just do the science and everything else is somebody else's problem. And I guess what I was trying to say is that if you're in that position there, and you're hearing a lot of comments from other people about, maybe you need to be worried about these things too, that may be telling you something about just trying to extend just a little bit what you think is your business. And what it is that you need to go to bat for. And where I think this is particularly crucial is in terms of like the future of life on our planet and in our solar system. So, and one of the tough things as an anthropologist is you're always kind of trying to tell people that, for example, the way you talk about life or the images that you choose about life, it literally does have an effect on what other people do with life. Those arguments can be difficult to quantify. I'm not doing this real well right here, right now, but what I'm trying to say is that, so if, for example, you're involved in technosignatures, you are actually often talking about a big story of life. It's usually situated within this large narrative of our relationship to life and where everything is going and all of that. So you are always telling a story about life. And if you're doing that, or if you're telling a story about the huge significance of what you do for humanity, without also kind of thinking about, okay, so where is my personal responsibility in that, or where is my program's responsibility in that? If I'm going to talk about the importance of life, what should I be doing about its future right here, right now? So that's kind of what I'm alluding to. Again, I'm not crystallizing it real well right now because I'm tired. But I would just encourage everybody to just think a little bit further about where those edges of your responsibility might be, especially if your own scientific community is strongly encouraging you to do that. And this is the anthropologist channeling for you, it's not coming from me. So how you do that, I would say, there's always common ground that can be found. Everybody has some kind of baseline concern. It's like, yes, I agree, we're all concerned about that. The dimensions that are further on, there's going to be a lot of variation, but there's always common ground to be had. And I think it is a really important time for the scientific community, particularly those concerned with life and with the future, to be at least banding together on some things. So that's a long answer to a really good question.
Thank you. I wanted to actually go back to something that Judge Tatel said just before this panel started, because I think it is really relevant at this. So he had actually put, when it was talking about echoing something that other people said about sort of rebranding a little bit for what this meeting is actually about. There's basically the search for the origin of the universe's life is sort of what a lot of us are doing that is not yet intelligence. It's sort of the step before intelligence. It happens to have a nice acronym, which is slightly different, and it's certainly known that you can change your the SETI acronym a little bit, maybe periodically it needs to be done. But it's sort of the search for the origins of the universe's life is what maybe more like what's been done with JWST and what Jeff talked about, and what Charles thinks is much more productive than actually looking for intelligence. But it's first the origins of life and then SETI. So maybe we should think about, because that's really there's a big fraction of us are not really looking for intelligence in this organization. They're looking for just life itself, and maybe that maybe is what's being thought about, is that's what should be appropriate. And that's something that actually at least might be newsworthy if we were to change the acronym for a little bit.
Gotta keep changing it to keep generating the news, right?
But
I just throw something out here where we were talking about the future, where the future might not be biological one. It's all AI and robotic. I mean, we seem to be biology focused here.
There's a really good book I can recommend on the Age of M by Robin Hanson. He was my professor at George Mason University.
To that though, there's something interesting. So often in studying the post-biological has been raised, lots of good modeling about how much more readily it would spread and how much more likely it is to be a post-biological universe. I always find that one a little bit curious because the idea that technology would completely supplant biology, I think you're more likely to see some fusions, and also, I mean, so is the technology gonna like literally just eat the biosphere completely, or is it gonna just start ignoring it? So I think there's always going to be this interesting duality, this interesting kind of tension, even if that should come to pass.
And there's also the presumption that biology precedes technology. So even if we're in a, quote, post-biological universe, that just pushes the question off in time. So now you have to ask about what was happening in the past.
And also, I think it's worth asking ourselves, is that even the right term if machines are something that come out of a biological process, and in some way they're a continuation of the process by which certain cells became organisms and organisms became, it might even be sort of a false dichotomy. Maybe in some ways they are life forms. They're just life forms with a different mechanism and a different origin.
Exactly. Just as we may be machines.
Right. Well, and we're bacteria. I mean, so.
Russ.
Clearly, identifying consciousness and intelligence is non-trivial. So I'm curious, since this panel is about thinking on 100-year timescales, how much time do you think will pass between the detection of a suggestive signal and the conclusion that it comes from intelligence or consciousness or whatever? We're talking, smoking gun or centuries?
I would throw that question open to the entire audience, because there are surely maybe people in the audience who have thought about this question. Jason, you want to?
I would guess it's going to go a lot like Astrometric planets that we saw from Alan earlier. That there's going to be a signal, and we're going to say that looks right, and a lot of people will be convinced, and then maybe decades later it'll falter, and then maybe there's another one. I think it's going to be a long, ambiguous.
So centuries?
Oh, I'm not going to guess on the time scale.
I think it depends on the specific characteristics, right? Because some are going to be a lot more indicative than others, any degree of structure, et cetera. But I think this principle of ambiguity is hugely important.
Well, it's back to the extraordinary claims require extraordinary evidence, so immediately people are going to say, well, is there another explanation for that signal?
One can certainly imagine a kind of detection that will be correctly interpreted as an unambiguous success. And one can imagine a lot of kinds of detections that will fall in the category that Jason was describing.
And there's a scenario that Cherkovich calls bare contact, which is you see a narrowband radio signal, and that's all you ever learn about. You know it's technological. That's it. That's all you got. And that could also be there.
Daniela.
Yeah, it could be that our concept of consciousness is completely flawed, and we might discover that later, or it might change completely from now to 100 years with the neuroscience and also more understanding on evolution of life. And to me, I feel like this concept of consciousness is really very anthropocentric again. And I don't see why other life forms could not have some kind of, certainly they have an adaptation to the environment which is superior to that of humans in some cases. So this imperative of life, I find it very interesting to reflect upon, because I think that's probably more interesting than the concept of consciousness itself. Because eventually consciousness might be just a result of this evolution, as as we already pointed out earlier. So this might also change a lot over the past coming century.
Thank you.
So this might be an obvious question. How would we narrow down the search for conscious life by looking at, say, for example, biosignatures, which may or may not be indications of sentient life present on a given planet? Has there any thought been given to that problem? How would we guide that search, or is it worth guiding that search?
Well, I would just say that I think there's been some thought given to this problem by philosophers, but the philosophers and the observers haven't really interacted, and how you would observe for consciousness, of course, is huge mystery. It's probably as good a mystery as what consciousness is. Dan?
Oh, we're talking about these different scenarios of detecting advanced technological life. I think the most likely scenario is just an artifact of their radar signal or something like that. And then you won't really know much about their culture, or their consciousness, or whatever you want to ask. And on the opposite extreme, you become, a member of the galactic internet, and you get access to all of their publications, and and then you can go through, if you're interested in the consciousness question, you could just say, you could read all that papers and how many species pass the mirror test and recognize red dots on their stomach, and how many species don't, and you know that about all the planets in the galaxy. So there's a whole continuum of scenarios, but I think the most likely thing is, we know we're not alone, we get this radar thing.
But you're saying smoking gun, right? What if it's the Lance Solaris scenario where they find a weird ocean, they don't know what the heck it is, they don't know if it's alive or not, and then 150 years later...
Right, I think that's very likely. They'll be ambiguous, and there'll be huge fights about whether this is natural or artificial.
Good. And these fights are, you think,
It'll
last a year
and we
or 100
we
years?
might be arguing about it in this auditorium for a long time.
I think sometimes you need time series data in order to evaluate, so if you've got local disequilibria that are evidence of intentional action, that could help, but it might unfold on very long time horizons.
We are right at the ending time for this panel, so I would like to thank all the panelists, particularly for staying on time. I would like to thank the organizers of the workshop. This has been a magnificent experience, and I would like particularly to thank all of you for being here to the very end.